Hello, good morning. Sorry, good afternoon. We'll get started at 2 o'clock. It's 2. Professor is here.
I'm ready whenever you are, okay?
Sure. Thank you, sir. Good afternoon, everyone. A warm welcome to the one who have joined this training program. It is very overwhelming to see we have this 1500 plus participants, one of the largest cohort we are hosting this today. Um, there are people across the country who have joined this training program, and it's very overwhelming to see that many of them will be taking their first step on this semiconductor domain and making a career ahead of it, be it research or going to the industries and the corporates. It's good to see the program itself talks about its enriching and the content which we have accumulated this in this program design for this, laying a very strong foundation in the fast changing domain of semiconductor. It's good to see the responses from the students and the faculty group out here. There are several different stakeholders who are doing this training program. Before we continue with the session, there are certain terms and conditions requested from the participants. We have already shared the details about this assessment and certification. Recordings will be shared throughout. PPTs will be shared as the faculty who are willing to share, because it contains the IPR rights. The faculty who shares will be sharing with them, and who are not willing to share, we cannot have any control over that. So please be patient. We'll be sharing all the requirement, be it the study material and the assessment details throughout. And one more request, the participants are requested to use the toolbar question Q&A for putting the question, and it should be more of a content driven, not asking any administrative and logistic queries here, so that the faculty should be very much engaged in having a meaningful and technical discussion rather than addressing the questions on administrative and logistic. Now, without much further ado, I would request Professor Vasti to take over, who is also the program director of this training program. Over to you, sir.
Thank you, Seema. Program director seems a little too formal. I am just a faculty looking after.
You are, sir.
No, nothing. Program director means like somebody's giving me director. Anyway, that's a, as you would call an administrative detail. So let us not waste time on it. All right, let's get started. Thank you all for joining. 1500 is really a large number. Thank you so much. In some ways, this program is actually was launched to cater to a demand, and it's very nice to actually see that the demand is actually increasing. Okay, so let me share my screen. So this first topic, somebody has his hand up. Mr. Venkateshwar Rao, if you have something burning question, please shoot while I share my screen. Okay. Seema, let me know when you see the screen. We good?
Yes. Yeah.
Okay. I'm deliberately sharing it in this mode. If somebody has a problem, please let me know. But if this works correctly, you should actually be able to go back and forth in the slides if you need to. Okay. So yeah, so just this is just a caveat. This training material I have actually created from multiple sources. Some of them I actually don't own the copyright for. What that practically means is you're welcome to use it for training and other purposes. But if you ever happen, but please don't reuse these slides for any commercial purposes, because ISC does not really have the copyright for much of the what I'm going to talk about. Okay. So I'm going to start talking about a semiconductor ecosystem. And the reason we want to start there is because semiconductor is a very big field. It means a lot of things to a lot of people. depending upon which minister you listen to, India is doing great in semiconductor manufacturing. But at the same time, we have a semiconductor mission that is trying to build more stuff. So what are we trying to build? What do we have? What we do not have? How does that the larger ecosystem sort of integrate with itself? Is the subject of today's discussion. The goal is that at the end of this program, you should be able to have an intelligent conversation with an industry person on what exactly ATMP is, what is a fab, what is a foundry, what is TSMC, what is Intel, and what is the difference between the two. This program is being organized at Indian Institute of Science, which by most metric is India's top-ranked research university. In some ways, it's interesting because I don't know your students, how many of you know the story, but actually ISC was actually set up on the recommendation of Swami Vivekanand to Jamshedji. Both of them were returning from a trip in the US and they happened to be on the same boat. This is 1890s. And Swami Vivekanand said, oh, you are getting all these factories, or you're setting up all these factories in India. Where will you find the people to man these factories? And he said, so what do you think I should do? He said, why don't you set up an institute? And ISC was born. Jamshedji actually never lived to, he gave the funds for the institute. His name, he explicitly mentioned that his name not be mentioned in the name. That's why I called Indian Institute of Science. There is no sort of indication of Tata's. That was his wish, but he never actually saw the institute get built. But the reason this sort of comes up for a full circle is that in some ways Tata is now setting up India's first fab. And the department that I hail from, which is Center for Nanoscience and Engineering, is actually probably one of the more important centers that are creating both the talent and the technology for semiconductor technology today in India. So in a lot of ways, 100 years later, but that vision did come full circle. Okay, so who we are, so the name center throws people off. We are not really a center in the classic way. We are actually a full-fledged academic department. But the reason we are called a center is because we are not a traditional academic department. We are interdisciplinary center. We have faculty from material science, physics, chemistry. We have faculty from electronics, of course, and many other disciplines, because semiconductor manufacturing is actually not electronics. It's a misnomer. You actually need mechanical engineers, material scientists, physicists in as much number, if not more, to actually make it happen. And for the simple reason that semiconductor manufacturing is a manufacturing role, and that requires those other skill sets. The second thing that makes us different is that we are home to India's largest academic foundry by some distance. Did I just lose? Okay, by some distance. We are an integrated facility, meaning we have both fabrication, characterization, and packaging. These words will make more sense at the end of this presentation. And lastly, we are an ISO facility. That basically means that we have certain standards of safety, performance, environmental responsibility, etc., that we uphold. Just some quick numbers. Other than those three large facilities, I think the most important thing that is on this slide that is probably worth mentioning is that we have a cadre of staff. While I hope to think that our faculty and students are the best in the country or best in the world, and I'm very proud of the quality that we have, but I think what makes us singularly different than pretty much any other academic fab that you will ever encounter is that our staff. So around 110 staff members manage these facilities that we use, and it is they who sort of enable a lot of the project and impact that we create. We of course do the usual publication, patents, technologies, etc., but we are extremely focused also on technology translation. And if there is ever an opportunity, maybe I can talk more about it. And last bit, which is probably the most relevant for most of you here, if at the end of the summer school you do sort of think, oh sorry, winter school, if you do think, hey, I want to get involved in semiconductor technology, can I get trained? Can I run a project? Can I come and do my master's and PhD theses here? The answer to all of those questions is yes, and that is this bit, that we actually are a national facility, meaning anybody in India can come and use it. In a given year, around 1,600 bright students like you come and use our facility, and we would be very happy if you would also join in. Okay. I put this slide up because it's important to set up context and expectation. This is what we are talking about when you're taking semiconductor manufacturing. When you think of a typical semiconductor job, I remember when I graduated many years ago, one of the top jobs in semiconductor that you could get was get a job in Intel. those jobs still are available. There is a very big pool of Intel engineers that are sitting in Bangalore. But what they are doing is they are not doing manufacturing. What they're doing is they're doing design. They are making blueprints for what these integrated chips look like without actually ever making one. Much like an architect makes a blueprint, but never actually pours any concrete. Our department focuses on, and what I'm going to talk today about, is semiconductor manufacturing, which is actually making devices like these. So these are some examples of devices that are made in our fab. On the left, this is a gyroscope. This is a version of this is inside your phone. This is what tells your phone when it sort of rotates. On the middle is a gallium nitride power IC. This does DC-DC conversion, AC-DC conversion. It's in inverters, etc. On the right is a heterogeneously integrated 3D IC, where each of these layers is a separate chip that has been sort of put on top of each other and interconnected. Bottom left is an RF device. This is for 5G, 6G communications. It's also for modern ultra-high power radars. On the right bottom is an opto-MEMS filter that is used for internet communications. The point, I guess, is that we actually make stuff, okay? So everything that you are going to talk about is about manufacturing. We're not talking about design. We're not doing cadence. We are not doing simulations. We are not doing Verilog. We are not doing VHDL. Those are things that typically happen in a design course. This is not a design course. This is a manufacturing course. All right. So the first question is, so why are we talking? I mean, what are we talking about, right? So many of you may know that India's first fab is currently being built in Gujarat. Tata Electronics is setting it up at an investment of 91,000 crores. This led to a slightly funny story when the Modi 3.0 came. One of the ministers, for example, was told about this project, and he was like, "What? 91,000 crores for just 2,000 jobs?" Then he did some internal math, and he said, "But that is several hundred, several crores for just one job. Why does that make any sense?" And then he was asked to quiet down, and then the conversation moved on. But it is worth asking that question: that why is it that India as a country is investing 91,000 crores in a plant that will ultimately just give jobs to 2,000 people? Like, what is so special about it? And the short answer is what makes it special is the area of electronics. Electronics is pervasive. There is really no sector of the economy that is currently unaffected by electronics. Whether you talk about agriculture, you're talking about smart agriculture. If you're talking about communication, you're talking about electronics. If you're talking about modern healthcare, you're talking about electronics. If you talk about Industry 4.0, robotics, IoT, all of these are essentially electronic advances. Recently, Operation Sindoor happened. People talked about drones, people talked about seekers, people talked about surveillance and reconnaissance, and all of that is electronics. If you're talking about energy transition, whether electric vehicles or solar cells or the batteries or inverters, everywhere you will get electronics in. So because of that pervasive nature, electronics at this point is a strategic resource. You cannot just think of it as just one more line ministry in a large number of other line ministries. Just like steel probably powers the industrial revolution, or steam powered the industrial revolution, the modern ecosystems will be powered by electronics. And on top, and electronics not only is big by its own metric. These numbers are at this point old. I should probably update these slides. But semiconductor manufacturing, somewhere along the way, IC industry as it's called, is around $575 billion. Let's just round it up. After a few years, let's say 600 billion. So semiconductor technology is 600 billion. Now that's a pretty large number. However, it does not quite capture how important it is because it underlies an even bigger ecosystem. So for example, tech industry, right? India is one of the huge beneficiaries of its tech industry. So many of our IT professionals bring in like basically get offer services which bring foreign exchange to the country. And that number, I find India's IT exports are, I think, several hundred billion. I actually don't remember what the correct number is. If you look at the tech industry on its own, I'm talking, when I say tech industry, I'm including Google, Apple, Facebook, Microsoft, Netflix, all of these combined. That is a 5.5 trillion or $5,500 billion industry. Just to give you context, India's total GDP is less than 4 trillion. So all of Indians together do not produce as much economic output as the tech industry does on its own. And This tech industry depends upon, and rather critically depends upon, the semiconductor industry. Without the semiconductor industry and its advances, the tech industry cannot go very far. Between the tech and the semiconductor industry, there's also an electronic subsystems industry. Now you're talking about people who make systems, computers, servers, phones. If you're like into cars, then people who make cars and subcomponents of cars, etc., etc. And that is a $2,500 billion industry on its own. If you can go back, the semiconductor industry also is built upon on top of other industries. For example, it's built upon an equipment and material base. A semiconductor requires very specialized equipment. It requires very specialized materials. That specialized equipment and material industry itself is 140 billion, which is a pretty big industry. 140 billion makes it larger than India's diamond export business. And finally, the bit that India has some presence in, which is softwares, like softwares for electronics. So these are the softwares that are being used in these design houses in Bangalore to create blueprints of ICs. And that itself is around $20 billion industry. So semiconductor is important. It's big. I guess that's the important 2 points. The third thing that makes it very interesting is that despite its size, it's actually booming and it's going to double in size. It's not every day that you look at a mature industry like electronics and expect it to double. Semiconductor industry currently, as I said, is around 580, and it's expected to become 1 trillion by 2030 or maybe 2032. So whatever semiconductor industry has done since 1940s till today in 70 years, it's going to do all over again in the next 7 years. And that's kind of a startling statistic. All this growth is going to be owned by someone. Someone will get this $500 billion of extra business. Why should it not be India? And that is one of the reasons that we are interested in it. What are we talking about when you're talking about semiconductor industry? Right now, I'm focusing completely on these IC chips. Once again, not design, manufacturing of IC chips. And IC chips come in many different forms, factors, and sectors. So the one that is most close to you and something that you probably have heard about a lot is logic, which is processors. These are Intel processors, AMD processors. These are also GPUs of the type that NVIDIA makes. These account for the largest lion's share of the semiconductor IC industry business of around 42% of that 600 billion. An equally important and very large segment of the population is memory. This is your NAND, DRAMs, so both volatile and non-volatile solid state memories, not hard disk, but everything else. And that takes another quarter of the industry. Together, logic and memory make up 2/3 of the business. And this is typically what is called Moore technology. So we will discuss Moore's law soon, but this idea of that, hey, chips always keep getting smaller and better every 2.5 years was the Moore's law. So logic and memory follow Moore's progression, and this is just us increasing scaling continuously more and more. Then there are a whole bunch of technologies that are Moore's and Moore technologies, which are not on the Moore roadmap. For example, I see some hands. I will give me some more. Let me come to an end of the section, and then we can take some questions. Then there are some power and analog ICs. For example, ICs that go into an inverter or go inside your battery chargers or go inside your adapters. These are also that are going in these EV chargers that are being set up all over the country. You can also, these analog includes communication chips, 5G, 4G, radar. Then you are also talking about optoelectronics. You're talking about cameras. You're talking about night vision cameras. You're talking about displays, sensors. All IoT and all industry 4.0 and all robotics requires advanced sensors, and that is a pretty big business. But despite it being big, it is still much smaller than logic and memory. And the reason I'm sort of highlighting this is when you start looking at what type of projects are actually going to come up in the country, you will notice that we are very heavy in logic and memory, and that is for this reason. While there are other technologies and they are pretty big, you see, 20% of 600 billion is not small, but it is still smaller cousin compared to logic and memory. And historically, India has had no footprint in either memory or logic. All right. Next, some terminology, just so that we are on the same page. Typically, ICs are made on silicon wafers. They sort of look like these circular things. And inside these circular things, you see these squarish looking fields. Each of those square looking fields is actually one complete device. So what happens is you take this wafer, you dice it, you just cut it into pieces, and each of these small squares is called a die. And that die is one device that you're going to sell it to a customer. But before you can sell it to the customer, you must package it. Packaging means you need to protect it, but also need to protect it in a manner that you can get the electrical connectors out. So this is what a packaged device, for example, looks like. If you open the cover, there is a small die sitting in the middle, and then there are very thin wires that are sort of taking the electrical signals out. Modern compressor chips will be much more complicated, but the basic idea is wafer to a die, from die to a packaged device. And this is what you call an integrated IC chip, this black color thing that you sell to the customer. Okay. Just 4 more slides, then I'll take questions. Now, this is what the next bit that I want to sort of get across is what is a typical semiconductor value chain. As a student, when you look at electronics, what you do is, hey, I need an IC. You go and search online and you figure out a data sheet, and this is what the data sheet does, and then you use a circuit, you build a circuit around it. Commercially, that is not how it actually happens. The really big players, for example, an iPhone, actually do not start their journey by looking at data sheets, existing data sheets. What they do is they first actually envision the product that they want to make. For example, the next iPhone. Then they take what are the features that iPhone requires and break it down into a system level design. This is not an IC design yet. This is a system level description, a block diagram. Okay, it needs to have needs to have an RF controller. It needs to have a memory controller. It needs to have a charging system. It needs to have a display. It needs to have a communication modem. It needs to have a CPU. It needs to have memory, etc., etc. So you break down what are you looking for in terms of performance. Then once you have a functional description of what you need, then you go to an IC design company. And if you're as big a company as Apple, then you don't use what is already available. You tell the company, you build me a chip which can do this functionality. Okay. So they tell Qualcomm or whoever is making their chip, or they tell Hynix, I need XYZ in this form factor, in this size, with this specification. And the IC design people say, great. So how much volumes you need? Okay, you need this many 100 millions. Fine, we'll make them. So they design the chip, which is another way of saying they create the blueprint. Much of this is done on computer-aided software. And all you actually have at the end of this activity is a thumb drive or a file that essentially represents what the design of the IC is. Now, a lot of technology goes into testing this, making sure you're not made a mistake, doing a lot of simulations. All of this is what is happening in the Intel Bangalore Center. Okay, this is all what is happening in NVIDIA. This is what is happening in the Apple's IC design team. Apple has started making its own IC. Once the design is final, then it's sent over to an IC fab. This is where the actual manufacturing happens. The difference between a fab and a foundry is just in description. A foundry is a service. So TSMC, for example, does not make any of its own designs. It just gets designs from NVIDIA and does the manufacturing. When you do that, you are called a foundry. When Intel does its own design and uses its own fab to make that design or realize that design or manufacture that design, then it's a fab. So it's a very small difference. The two can be interchangeably used to first order. Once the IC is done, remember, it is still not yet a packaged device. What needs to happen is somebody has to dice it, somebody has to package it. That typically happens in a separate facility that is called an IC packaging facility. So if you have heard of names called ATMP, so the Micron facility that is coming up in Gujarat is an ATMP facility, assembly, testing, marking, and packaging. What they are going to do is they're going to make the wafers in Japan, ship the wafers from Japan to the facility in Gujarat where all of this dicing, etc. will happen and packaging will be done. You might have also heard of an OSAT facility. OSAT facility is the type of facility that Tata Electronics is setting up in Assam, where they will not, it's not an in-house thing. It's not like Tata is making the wafer somewhere else. They will go to any company, for example, NVIDIA, and say, you give me your wafers, I will package them for you, and I will send you the packaged ICs. So it's an outsourced semiconductor assembly and test. So functionally, whether you own it, if the same company that's making the wafer also does the packaging, it's ATMP. If a different company is doing it, it's outsourced and it's OSAT. Once the IC is made, then you have these black thingies. You can buy them. They get sent to PCB manufacturers who basically do the assembly. So when India says we are making iPhones, what we are really doing? Are we doing everything from design to fab to packaging? No. What we are actually doing is assembly. These PCB boards and sometimes PCB assembly board sub-assemblies are actually coming from China. We're putting all together. Maybe we're doing some soldering. We're making some connections. There's already a design that Apple has given us. We just do exactly this and just assemble it all together. And then finally, we put it inside a container, do the final testing so that the system works, and ship the product back to Apple. This is what a typical supply chain looks like. All right. Now, what is the gap? India historically has had companies like Apple who have been doing hiring and doing their research work. So to some extent, the system level designing, to some extent, was happening. It's not happening for our own products, but we are doing it for big companies. We are also been doing IC design. India is actually a very large IC design house. We have probably the most number of IC design engineers across the world. Once again, we don't necessarily own the IP, just like in IT, but we do a lot of back office work. What India did not actually have is anything from fab to assembly. So recently, when we started doing the iPhone assembly, we got assembly. And now India is one of the very big makers of iPhones and other cell phones. What was still missing was the fab and the packaging, and that is what these Micron and Tata facilities that are being built will have. This is what an IC fab actually looks like from inside. You can see it's a very specialized looking environment. The people are wearing these white color suits because this is a very ultra clean room, and humans are the dirtiest part of a clean room. So you typically have you're completely covered so you don't contaminate anything. We also do things like lithography, which we will discuss later, and that requires even more specialized clean rooms. Point is, because of its scale and because of its technology, these things are ridiculously expensive. These pictures are for an Intel fab that was built in 2010, and at that point it cost 10 billion. Today's state-of-the-art fabs cost somewhere between 30 to 40 billion, if not 50 billion. Packaging is cheaper. And that is one of the reasons why most of the facilities that are actually coming up right now are actually packaging and ATMP and OSAT facilities. The requirement for both technical detail and training are less severe. Other than these two big weights, which is fab and packaging, then there are smaller things that we have to worry about. For example, there's a whole bunch of suppliers who deliver wafers, who deliver materials, who deliver chemicals, gases, wafers. So that is this bit. Then there are companies like Applied Materials and Lam Research, which create equipment. These companies used to do the manufacturing. So that's actually a pretty big sector itself. Then we have already discussed design and the software that are used for the design and those software development. So all of these are also pretty big parts of the ecosystem. And if India has a fab and a packaging ecosystem, then it's probably going to be that India will also have a slice of these other ecosystems as well. Last bit, so what's the challenge? Other than the cost and other than the ecosystem, most people think of talent as the top problem. The world is going through a demographic change. Traditional big players like Taiwan, Korea, Europe are reducing their populations. There are not as many engineers as they wish they need. And this is where India has an opportunity. And this is why programs like today's are kind of important. Okay, I know there are many questions and I'm running a little late. So let me just ask two. So raise your hands. I'll take two questions and then we can take the rest later. Right, Akash.
They won't be able to unmute and talk, sir. You can
Okay,
take the
we
two
do.
questions from Q&A toolbar.
Okay, I don't see it. If you
One
see
question
it,
is, what is the role of mechanical engineering in semiconductor industry?
oh, humongous. Mechanical engineers are the one who are basically running the ACs, the equipment. The equipment design is essentially a mechanical thing. Robotics that is used inside the fabs is again a mechanical engineering thing. So, I mean, over this course, you will sort of see many such examples. One more question, Seema.
Another question is, will India have semiconductor material manufacturing industry or only chip design? Your view on that?
Oh, we are investing. So short answer is I hope to God, yes, because I have bet my career that will happen. I think so. India is too big a country not to have some part of this. Okay, let's keep going. So we have already discussed, right? So India is making investment. So that's why government has basically launched the India Semiconductor Mission. This was a few years ago. At this point, actually, the first phase is already done. There is talk about Semiconductor Mission 2.0. The idea was that we tried to pull off a Maruti. We are exactly doing the same thing that we did with Maruti. The government said to all the private players that fine, why don't you set up a factory here? You bring your technology and we will pay a huge part of your setup costs. So 50% of your cost of setting up the equipment will bear out. Many of the states joined in and added another 10-20%. So at this point, the Tata fab that is being set up has been paid by state and central government to the tune of 75% or something like that. So the plant is essentially coming for free. They just need to run it. That is the goal. And the hope is that the first few people will come because of this incentive. But once they set up shop, once the ecosystem develops, then others will come simply because India has the talent, India has the scale, and India has the ecosystem. The only problem is India is not the only one who has this bright idea. We have invested 77,000 crores, which is give or take $10 billion. There are many people around the world who have done the same thing. Europe has a CHIPS program, America has a CHIPS Act, China has a mission program, Japan has a mission program, and many of these countries have much bigger budgets than we do. So as we speak, India is building one fab and other countries around the world are building nearly 30 fabs, if I remember correctly. So we are not alone, okay? But anyways, what is being announced is the two big things is the Tata Fab and the Tata OSAT, which together account for nearly 130,000 crore rupees, mind-boggling number. There are smaller facilities of 3 to 5,000 crores that are coming up in packaging elsewhere, and Micron has a 7,000 crore investment. So overall, there are basically 10 projects that are coming in the states of Punjab, UP, Assam, Gujarat, Telangana, and Odisha. Right. I am not privy to any of these details, right? I don't know what Tata is thinking when they launch these programs, but I can read the news and I can put two and two together. So in my opinion, this is basically what is happening. So currently when an iPhone gets made in China, the way it works is, again, Apple basically designs the products. It does the IC design with companies like SK Hynix and Samsung and etc. It gets fabricated in foundries like TSMC. It gets packaged in companies like Amkor, and it gets assembled by Foxconn. What has happened in India in the last few days is a slight change. Tata has started buying a lot of design companies, for example, Sankhya and Tejas Networks. Tata has decided to create a foundry. Tata has decided to do packaging or set up a packaging. And Tata has also purchased the Winstrong facility where they make iPhones. So what is Tata basically trying to do is basically trying to give Apple an alternative supply chain that is not based in China. Okay. All right, talent needs. So this partly answers the question that you basically raised that, hey, where are these things needed? Basically, this is what a typical fab of the type that Tata is setting up. This is not packaging, but this is fab Tata is setting up. So it will take around 2,000 people. And just 1 second, let me see if I can make it big. Cannot. Take it. Content only. Not working. Okay, sorry, my bad. So where people are needed is people are needed in manufacturing, people are needed in support services, people are needed in robotics, people are needed in operational research, and people are of course needed in R&D. But the point, however, I do want to sort of highlight is key. Fab is very diverse. It is not electronics. And if this is one message that you should take home from today's presentation, this presentation specifically, it is that semiconductor technology is not electronics alone. Yeah. So I've talked enough about ecosystem. Now let's get to a very interesting question, which is what makes electronics so powerful? Like it is pervasive, it is everywhere, it is powering the world. I mean, there are many technologies, many interesting technologies are created. What makes electronics so special? And the short answer is scaling. And I would like to talk a little bit about what scaling is and why is that so powerful. Okay. So microfabrication, basically, as the name suggests, is about making things small. Okay. But people don't generally have a sense of size. So let's start there. So on the right is a width of a human hair. Okay, 100 micron. Human hair is probably the smallest thing we can see reasonably easily. It's around 50 to 60 micron in thickness. Some of the largest devices we make in our center, and our center is no more, definitely not the cutting edge of making small devices, is 100 micron. So some of the largest thing we make is about the width of a human hair. Okay. And in fact, the features on these devices are actually much smaller, much closer to 10 micron than to 100 micron. Intel, which is a world leader, of course, makes much smaller devices. This is an Intel Broadwell chip, which was a 14 nanometer technology node. This at this point is a 15-year-old technology. So not even cutting edge today. This is a top view of that IC chip, and you are looking at a scale bar of 800 nanometers, which is let's approximate it to 1 micron. So from this picture to this picture is a factor of 100. Okay, so you have zoomed in a factor of 100. And if you look at here, no device is as big as 1 micron. In fact, most devices are only 100 nanometers or so, and the smallest devices are even smaller than that. And the smallest features on the smallest devices are smaller even still. We will talk about what is the current state of the art in terms of 4 nanometers, 2 nanometers. What are we talking about later? The point is we really make things small. Modern devices are somewhere between 1,000 to 10,000 times smaller than the width of a human hair. And where is it ultimately all going? We are basically getting to the limit of the atom itself. This is graphene. This is one of the things. This is one of the deposit. This is something we deposit in our center. What you're actually looking, this wrinkly looking thing, membrane thing that you see on the screen is actually 1 atom thick graphene membrane. It's amazing to me that we can even see this, right? I mean, you can actually see the folds in 1 atom thick layer. So this is where we are going. This is how small we wish to become. The fact that we can make things small, however, I mean, it might excite me, but you as a taxpayer and you as an investor would ask the question, so why should I care? As in, so what? So what? So the next bit is to answer the question, so what? Normally, all technologies have a cost performance trade-off. Now, what that means is that there are many ways of executing a problem or executing a solution. But in general, if you want best performance, you need to pay a special cost for it. So both of these vehicles will take you from point A to point B, but definitely the Formula One car is way more expensive. So the cost bit is typically on a log scale, right? Like it's not a linear scale. Electronics is the only technology I know where this cost performance trade-off actually does not work. Electronics is the only technology that I know where every 2.5 years a new technology will be created. It will be cheaper and it will be higher performance. That is unprecedented. And it's not just that it has happened once, it has happened consistently for the last 70 years. And that's what makes it so impressive. That how is it that every 2 years we make something better and somehow magically it is also cheaper? And the short answer is scaling. And I will try to sort of run through the mathematical argument for why that is. So every time we go to a smaller node, we figure out how to make devices smaller. There is an additional extra cost. It doesn't come for free, right? Clearly, making things at 130 nanometers is cheaper than making things at 14 nanometer. On its own, this is normal. This is what happens with every new technology. Making a better car is more expensive. But when you look at what this smaller size accomplishes, every time you reduce the size of a transistor by, say, 70%, 30%, so you go from 1 to 0.7, you actually reduce area by 50% because length into length is area. So because it scales by a square on a how much area needed per transistor basis, every time we scale the device, we actually reduce the size it takes on the real estate it takes on the silicon wafer. And that allows us to pack in more transistors, which improves performance. But at the same time, it allows us to reduce the cost of that transistor for functionally doing something, for example, switching a bit or storing a piece of information as a memory. The amount of real estate that we take on the silicon keeps on reducing every time we do the scaling. And that is what allows us to scale the cost down. So every node basically provides better performance, but at the same time takes lesser silicon real estate and hence on a per transistor basis, cheaper than the previous generation of technology. And that is what makes semiconductors so much more powerful. And here are some examples to just sort of drive home the point. Let's take example of another brilliant technology that is very integral to our current way of life. For example, a car. Cars have improved massively over the last 50, 60, 70 years. But how much have they reduced? Have they increased and have they reduced in cost? Not really. Inflation adjusted, cars these days compared to 1930s are around 4 to 5 times more expensive. The society is 10 times more richer, so overall we can afford more cars. But on its absolute sense, cars have become more expensive. They have become better, but more expensive. Compare that to the cost of any electronic product, whether it's processor, whether it's transistor, whether it's data, whether it's memory. Everything has fallen not by 3, 4x. It has fallen by 3, 4 orders of magnitude. They have reduced in cost by 10,000 times or a million times. Those are unheard of numbers. Which other technology allows you to reduce cost by 10 to the power 4, 10 to the power 5? That just doesn't happen. Similarly, performance. Cars have improved over a period of time. The mileage, that's one common metric of cars, right? Mileage has improved. How much? 3 times. That's great. How much has electronics improved over the last 70 years? 10 to the power 4, 10 to the power 5, sometimes 10 to the power 6 times. Which other technology gives that kind of improvement? Millions, billions. And all of this while being extremely reliable. Okay? Actually, reliability I'll come to in a minute. And all of this at the same time becomes more portable, smaller in size, small in weight. The first ENIAC memory, which stored 36 kilobits of RAM, just to be clear, this is bits, not bytes. So 36 kilobits is 4 kilobytes. That is one empty notepad file. It used to weigh 17.5 tons. Today, who cares about a 4 kilobyte memory if you have terabytes in your thumb drive? And by all of this, while being remarkably stable, the electronic systems that US built for its nuclear infrastructure still functions today. It uses floppy disks and it still functions today. If you want to build it for endurance, electronics can be remarkably enduring. A car will break down if you drive it without servicing for, I don't know, 10,000 miles. Well, computer chip, if designed for endurance, will basically run for 30 years without you having to look at it. Electronics can be remarkably enduring. Okay, time for maybe 1 or 2 questions. Seema, pick.
There was a couple of questions related to, I'm coming from a civic engineer, I'm coming from a chemical engineer, I'm coming from a mechanical engineer, how it is helpful for me to do this semiconductor fabrication.
The answer to all of this is why don't you go through this whole thing and then you will yourself see where it is useful. I mean, it's just the content itself will tell you, you will see stuff that you use every day. Anything else?
Yeah, there were a couple of questions. Are we processing the raw materials required in the supply chain for semiconductors, pure silicon or pure germanium?
No, but that is being changed. To my knowledge, I have knowledge of some projects where those are where India will start producing some polysilicon and silicon wafers. Short answer, however, today is that we are not competitive. China just does it more cheaply. Okay, let's keep going. So what makes it, so why is scaling so important, right? And everybody knows Moore's law, and I mean, I think it's the most overused slide in the world. So I don't want to spend too much time, but I do want to get to what in my opinion is the more interesting thing is something called Dennard's law. He should be more as well known as Moore's. So what Dennard basically showed in a theoretical paper, by the way, not theoretically, it was theory plus experimental paper. It was at IBM, and he basically used semiconductor device equations that everybody sort of learns in their device course. And using those equations, he proved a very interesting point. He said, you know what, guys, if you just take a device and make it smaller, you will improve it in virtually every metric that is important for data processing. Let me say it again because it's important. He basically showed if you take a device, just take any device and just scale it down, just shrink it. Keep the electric field the same, just shrink all down the dimensions. Then the basic mathematics showed that the device will be better in pretty much any metric that is important for data processing, for digital memory and logic. And that is a remarkable statement. And this is basically the technical driver that drives microfabrication, because this basically means there is a clear performance improvement guaranteed to be gained if you can make devices smaller. And this has proven true for the last 70 years. This is what is called constant field scaling. I don't want to bore you with math because this is electronics engineering and this is not the goal. I just want to sort of highlight that if K represents here the scaling, so how much smaller you are making. So K is more than 1. And if K is more than 1, then you can see that either all the matrix either remain 1, which is no change, or become smaller. It turns out this type of scaling, however, was physically very hard to do. So there were some deviations. We'll talk about deviations. The other bit that is important to understand is this scaling only is relevant for digital electronics. This is a detail that most electronic engineers also miss. Dennard's law only is relevant for logic and memory, and that is why those two have been taken scaling to the extreme. Traditional analog electronics, for example, or which is communications or sensors, don't actually benefit that much from scaling. The only thing that gets better is speed, which is important. 5G, 6G run at higher speeds, so they benefit a little bit. But there is no fundamental importance in scaling there, and that is the intuition why, if you look at, for example, the op-amps that were made in 1970s, those op-amps are not thousands of times worse than today's op-amps. Today's op-amps is only marginally better than those, because analog electronics does not benefit as much. Our sensors are not thousands of times better than before. They are just marginally better than before. So analog electronics is much like traditional technology, where the improvements happen, but marginal improvements happen. The really record-breaking improvements are in digital. This is also what explains where people ask the question, okay, what is India building? And we say, oh, India is building a 28 nanometer fab, and 28 nanometer is 30-year-old technology. For many other types of fabs, for example, for power electronics, sensors, optoelectronics, there is no node, there is no 28 nanometers. It's an irrelevant question because they don't benefit as much. They just want to buy the cheapest technologies so that they can manufacture their IC. Many of photonics chips can be very easily made at 180 nanometer and they don't need to be scaled down. The state-of-the-art night vision cameras don't require anything smaller than 1 micron lithography. The state-of-the-art 5G, 6G devices do require some advanced lithography, but again, not state-of-the-art, really, really cutting-edge 2 nanometer technology. Okay, moving on. This was the point I was trying to make, that real-life scaling proved to be a little bit more complicated. Dennard did a very simple case of constant electric field scaling, but there are many things in life that don't scale very well and hence could not follow Dennard's law. For example, Dennard's point was, let's scale the supply voltage. So we start at 21 volts, and if we kept scaling the voltage just like we kept scaling the device size, at this point we will be running on millivolts of power. But reality is we do not run on millivolts of power. Power supplies do not scale very well. There are fundamental reasons for it. Band gap doesn't scale well, noise doesn't scale well. So supply voltages have reduced. We are at 1 point something volts these days, but it has not fallen thousands of times. The other things that don't scale, for example, are oxide thicknesses. Once the thicknesses really went down to 1 nanometer or 1.5 nanometers, we are just talking about 10, 20, 30, 40 layers of atoms. It was not possible to scale them any further. So oxide thicknesses stopped scaling at some point. In fact, at some point, even feature sizes stopped scaling, meaning that when you today hear about IBM is launching a 2 nanometer technology, you can ask yourself the question, what is 2 nanometer? And the short answer is probably nothing. In fact, that is a separate topic that we will sort of discuss as its own slide, that what does that number even mean? What do we mean when we say we are at 28 nanometers or we are at 2 nanometers? All right. The other version of scaling is something called constant voltage scaling. This is basically saying we'll not keep the electric field constant. We will keep the voltage constant and then just reduce the size. When you run the math under these constraints, the math comes out a little different. In this case, many things do become better, but there are a few things that actually become worse. And one of the more important ones that actually get worse is power density, meaning that the chip runs hotter. And this sort of explains your personal experience if you have with computers, that these days modern chips just require a lot more cooling than older generation chips did 30, 40 years ago. And that is because we are closer to constant voltage scaling than we are to constant electric field scaling. Okay. All right. So heat is an issue. Which brings me to the next most important slide. What is scaling? Like, what are we actually reducing? So the simplest version, which was the old version, was simple Dennard scaling. So what they did was from 250, they basically figured, okay, let us reduce the size by 30%. If you reduce the size by 30%, then it's a multiplier of 0.7. So 250 into 0.7 is 180, 180 into 0.7 is 130, 130 into 0.7 is 90, etc., etc. So each successive generation essentially is just a multiplier of 0.7. That is the ratio they just chose to be the right ratio going forward. Okay, that lets every generation let us try it to be 30% smaller. Why 30%? Because if you reduce both the dimensions x and y by 30%, then the total area reduces by 50%, and that is what this is. 0.7 into 0.7 is 0.49. At some point, what they were basically reducing were three things. One is they were basically reducing the distance between two features. For example, you have one metal line and you have a second metal line, and you are trying to reduce the distance between them. The third thing they were trying to reduce, the second thing they were trying to reduce was metal pitch, which is the thickness of the metal line, which is how wide each metal line was. They also were trying to reduce the width of a gate. Now, gate is an electronic term. You don't have to worry about what it means, but basically this represents how small the device is. Up till around 90 nanometers or so, what they were actually representing by saying 90 was actually what is the smallest width of a feature on the device. So it was really something on the device that was that small. But modern devices after 90 nanometers, this definition has become much more fuzzy. And the reason it has become much more fuzzy is because we have realized that scaling is not the only way to make an improvement. For example, we can make improvement in systems. When Intel first launched its device, it was just a PMOS device. It was not a CMOS device. Then Intel figured out how to do NMOS, and then Intel figured out how to do both PMOS and NMOS on the same chip, and that is what is called CMOS. This sort of reduced power consumption dramatically compared to both PMOS and NMOS, and that was a structural systemic improvement that does not get quite captured by simply reporting geometric scaling, right? What else have we scaled? For example, this is what the cross section of a typical device looks like. Okay, all the devices are on the silicon layer, but all these devices are connected by a network of metal lines, and all those metal lines are not in one layer. They're actually multiple layers of metal lines. Think of these as roads and over bridges and under bridges and over bridges, over bridges, just to get the information flowing all over the place. How many of these metal lines we have has consistently increased every generation, right? These days, I think we have something like 13 or 15 metal layers. So every time we added a new layer of metal, we added a new level of hierarchy of highways, and that improved the device performance. Again, that is not something that gets easily captured in just scaling. Then there are a whole bunch of other things. Some of them we will talk about in this tutorial, which is, hey, we added new lithography technology, we added new isolation technology, we added silicon germanium, which added strain inside the device, and that strain improved performance. We changed the gate material from low K to high K dielectrics. We changed silicides to less conductive to more conductive silicides, etc., etc. So many improvements that happen on the chip level don't adequately just get captured by saying, hey, I made it smaller. Smaller is a very big part of it, but it's not the full story. So what currently happens is we have an idea of what performance improvement we are looking for. We have historical data. We know how much extra performance we were supposed to get from each node. So we know what that number is. Now, as soon as we hit that number, we say this is the next generation. Okay. So, for example, this is the IBM's 2 nanometer process. You are looking at the cross section. What is 2 nanometers? The short answer is nothing. It's a 3D device. I don't know what is 2 nanometers. It has nano channels in it that are 5 nanometer high, that are 40 nanometer broad. What is 2 nanometer about it? Its performance is like a planar device that is 2 nanometers. So in that way, 2 nanometers is just like iPhone 16 or 17 or 18. It is just telling you that we have moved ahead. it does not represent geometry anymore, because geometry is just not capturing the complexity of this three-dimensional looking complex advanced device. All right. Just I believe my last slide. After this, I am now ready for questions. I think I have 5 minutes. Shoot. All right.
So there is a question.
Uh-huh.
In a recent past, there has been a breakthrough in photonic conductors, where now they are actually able to remember the bits similar to silicon-based semiconductors. So why are we betting on silicon semiconductor rather than we can focus on more on advanced conductor? Your view on this?
Short answer is follow the money. This is the answer. 2/3 of the industry is still silicon. Does photonic have a place in it? Absolutely. Do we focus on it? Absolutely. Indian government is willing to host a photonics fab. A photonics fab requires 1/10 the investment, but it also services 1/10 the market. It is just what accessible market we are talking about. Memory and processing, just we require a lot of it, and photonics not as much.
Which parameter becomes better in case of constant voltage scaling?
Many things, for example, speed, etc. I mean, if I go back here, speed, etc., the number of devices per unit area, all of those things are still getting better. The gate capacitance improves, the delay still improves, reduces, which means the devices run faster. Those are things are still fine. It's just the devices run hotter.
Another question, sir. 14 nm technology, what does it mean?
What does it? I mean,
Mean.
that's what I'm trying to get. There is no unique answer. It's when you say TSMC's 14 nanometer technology, it is TSMC's version where they have basically made certain improvements in their process, certain improvements in their devices to achieve a certain performance, which is like a 14 nanometer transistor would have. Each person, I mean, this is TSMC's version of it. This does not have to be compatible or equal to the IBM's 14 nanometer. It's just a collection of, I guess it's just a technology node that achieves a certain performance. The end.
Sure, sir. Since constant voltage scaling causes power density to increase at advanced nodes, how do spacecraft electronics manage heat in an environment with no convection? Are there semiconductor level design techniques to reduce thermal stress for the longer duration missions?
You don't necessarily need, not everything requires advanced scaling. That's, I guess, what I'm trying to say, that many things that are analog, like sensors, communications, you are completely fine making 180 nanometer nodes. There's a lot of manufacturing that happens at so-called legacy nodes. Tata is setting up a 28 nanometer fab. On its paper, it's so old, no NVIDIA chip will get made in it. But many chargers will be made in it, many communication chips can be made in it, many, I mean, your set-top boxes, right, which get your signal from the satellite for your TV, all of them have chips. All those chips can be easily moved in the Tata fab. So not everything needs advanced ultra high technology. It's a matter of selecting the correct answer.
Another question from Vidhi, sir. If shrinking makes digital circuits better, why doesn't the same thing happen in analog circuit? Your view?
No, it does not, because the mathematics is slightly different. So, I mean, now for that, you sort of have to read his paper. Uh, why is it that digital electronics benefits and analog doesn't? But the simple answer I can give you, for example, is just look at transconductor, right? If you're an electronics engineer, transconductance does not actually scale at all. You can make the device smaller, W becomes small, L becomes small. Actually know how to make this higher unless you change the material completely.
How it is decided when to add more metal layers? The last question.
I mean, this is not decided. So these are now questions of how there are people who are very advanced, who are fellows at these places like TSMC and all, who basically create the roadmap. You know what? This is where we are today, and we need to improve X, Y, Z to get to where we need to for the next node. And these are very confidential, very strategic choices that they choose to make. And companies who bet wrong die. I mean, the classic example is TSMC was not the world leader. Intel was the world leader. Intel selected the wrong set of things to focus on. For example, they did not focus on extra EUV, and they got left behind. And Intel is still struggling after so many years. Same thing happened with Global Foundries. Global Foundries and Intel were competing, and Global Foundries made a wrong bet. They chose to go in a certain direction that proved to be a wrong answer or a bad answer, and they have since not recovered. So you have to, I mean, there are people who make these choices, very strategic choices, and they are worth their weight in gold.
That's all, Professor. So far, so good.
So how does it work? We take a 2-minute break or we just keep going?
Take a break, sir. It will be good for all of us.
Okay, so 3:05 or
Yeah.
when? 3:02 or
3:05 is good, sir. 3:05 is
3:05?
good.
Chalo, ठीक है.
Yeah. Thank you.
Yes, sorry, Seema.
We'll get started, sir.
Correct.
Yeah.
So what I will now do is basically go over the whole process of making a microchip. Okay. Now, a typical advanced microfabrication chip has like over 1,000 or 2,000 steps. There's no way we can go through all the various varieties. But what we can do is look at the generic ones, for example, deposition, etch, lithography, etc., and talk a little bit about it. And we will actually go into details of each of these steps later. But before I get into the weeds, I wanted to, for example, show you the forest so that you can at least appreciate what's going to happen. Now, this will also have explain to some of you why mechanical engineers, material scientists, etc., come in, because many of these concepts of stress, yield, etc., are actually not electronics concepts. They are much more mechanical or material science concepts. Okay, let's get started. So overall, this is the way I categorize all these processes. So you start with the substrate. Okay, substrate in this case means the wafer, the silicon wafer on which devices are made. And there's a whole bunch of technology sort of goes in how to make this substrate, what are the characteristics of this substrate, and then modifications that you do to this substrate. Okay. The next bit is that in general, a blanket substrate is not useful. You do deposition. You basically deposit films across on the substrate through various chemical and physical methods. Blanket layers on their own are not as useful. So you in general need some patterning technology, that is basically lithography, where you take that deposited layer and create features on it. So we'll discuss that. And finally, once you have made the pattern, then there is some way of subtractive process where you remove material. So this is additive, this is subtractive. So whatever you have, whatever design you have created, whatever pattern you have created on the top of the wafer actually gets transferred to the pattern layer. And then this is not just done once in a fab. I mean, this is done multiple times in a fab. This sort of routine of modification, deposition, patterning, etch, modification, deposition, patterning, etch keeps sort of happening literally 1,000 times before an actual chip comes out. Okay. The other part of language that I want to introduce is this term called FUL, BUL. It basically is front end of the line and back end of the line. I got this image from Wikipedia. You can sort of zoom in if you want. Basically, what it shows is, sorry, I did something. Basically, it's a cross section of a device. So if you zoom in the bottom end, this is the silicon wafer, and you see this silicon device. Silicon devices typically are very sensitive to metallic contamination, something that we will touch later. Because of that, as soon as you start depositing the first metal, from that point onward, the wafer is considered dirtier. Okay, and that is what is called back end of the line. There are certain restrictions that you need to follow when you are dealing with back end of the line in terms of how hot you can take the temperature, what type of processing you can do. Front end of the line is the cleaner end of the processing. This is typically the first few bits of processing you do. Most of the time, the actual device fabrication happens in front end of the line. So that is what these things mean. Front end of the line is the first few steps, typically cleanest part of the process. Back end, and typically without metal. Back end of the line is the dirtier part of the process, typically happens later in the device fabrication and invariably has metal in it. All right. So let's now talk about substrate. So typically, unless specified otherwise, the default material for all electronic manufacturing is silicon. While there are options like gallium arsenide, gallium nitride, silicon carbide, and some of them are part of technology roadmaps, 95% or 99% of IC chips are made out there are based on silicon. Anything that can be done with silicon is typically done with silicon. And the reason for that is the maturity of the process of the product. It's very cheap, it's easily available, we understand it completely, and it is available in very large volumes. Silicon solar cell industry also uses silicon wafers. Typically, these are circular in size. Why circular will be obvious when we discuss how they are grown. They are typically 200 to 2000 microns thick. That's why, because they are thin and round, they are called wafers. The singular thing that you need to understand about semiconductors, IC wafers, is they're extremely pure. A good silicon wafer is easily parts per billion pure. Silicon material is the cleanest material we know, like the purest material we know how to make as a civilization, other than helium. So helium and silicon are the two most pure things we know how to make. State-of-the-art silicon is 99.9999999% pure. Okay, so ridiculous levels of purity. In fact, keeping this silicon pure, like making it pure in the first place and then keeping it pure, is basically why we need clean rooms. This is the clean room in ISC. If you ever visit for advanced training, I urge you to look at it. Basically, clean rooms are around 1000 to 10,000 times cleaner than the room that you're sitting in. And you need these clean rooms because you need to maintain purity. One of the dirtiest things inside a clean room is actually the human, because humans create particles all the time. To prevent the clean room from getting dirty and the wafer from getting dirty, typically people are put inside suits. These are called clean room bunny suits, and they prevent, these are not to protect you from the wafer, this is to protect the wafer from you. Okay. Okay. Once you have decided what the substrate is, mostly it is silicon, then you have to start changing the properties. And one of the ways in which you can change its properties is by depositing a film. The canonical way of depositing a material, and again, the same question with hands, we will take it, say 5-6 slides from today. Okay, is called chemical vapor deposition. The basic idea of a chemical vapor deposition is fairly simple. You take an enclosed space, so there is a chamber wall, you see this furnace with a quartz tube. You put your wafers inside. Then you heat the whole thing up so that the wafers will get hot, the tube gets hot, everything gets hot. And then you flow a certain chemical that can react to form the material that you wish to deposit. So supposing you wish to deposit silicon, then you flow a chemical that will react with the heat and form silicon. Such materials are called precursors. If you when that just basically the English of saying what is there before. So before silicon, the chemical that is before silicon is the chemical that forms silicon. So precursor. Those of you are from chemical backgrounds or chemical engineering backgrounds, this is not news to you. I mean, this is classic chemical vapor deposition process. It is routinely used by companies like Shell to create petrochemicals and plastics and various types of materials that we all use in our day-to-day. The same technology has been channeled in this case for semiconductor applications. However, the understanding, the mechanics, the concepts of gas flow, reaction chemistry, reaction dynamics, etc., is one-to-one exactly the same, and that is why such people and chemical engineers are routinely needed in semiconductor manufacturing. All right, going forward, when done well, silicon vapor deposition can be remarkably high performance. In fact, if you want a device quality film, if for some reason you need to make a device in a film, the default method to deposit that is through chemical vapor deposition. This is a reactor that I was trained on back in my grad school at Princeton. This is a student reactor, student built, student maintained, so definitely not state of the art. But even in this reactor, I hope you can appreciate, this is the layer of silicon that we have deposited on top of existing silicon wafer. This faint line that you actually see, this is the boundary. Okay. So even in a student maintained reactor, when done right, you can actually get near perfect clean surfaces that you cannot see very easily. And even if you can see, you need transmission electron microscope. You can look at this small dotted region. This is, you zoom in and these dots that you see are literally atoms. You actually are seeing each silicon atom that is sitting in its perfect place, and you know it is in its perfect place because you can take the electron diffraction pattern and you get an exact accurate electron diffraction pattern. Those of you who are from material science or physics background would notice that electron diffraction or XRD are routine things that you do to material analysis, and that is what we also use to evaluate or sort of characterize materials in semiconductor manufacturing. Hence, those kind of people are needed. So chemical vapor deposition when done right, is remarkably high quality. You can also deposit disparate materials. You don't have to deposit silicon on silicon. You can, for example, deposit silicon dioxide on silicon, and that is routinely done. In fact, silicon dioxide silicon interface is special. It actually is the reason why silicon is the dominant semiconductor. The first semiconductor was actually germanium. If you go back and look at history, the first transistor was demonstrated on germanium. Germanium arguably has slightly better electronic properties. What germanium, however, doesn't have has as good a quality insulator as silicon dioxide is to silicon. Silicon dioxide interface for all practical purposes is defect free. And that is rare and surprising because the silicon dioxide that we are talking about is actually not crystalline, it's amorphous. So the stuff that you see on the top, you don't see any structure because that silicon dioxide is amorphous. On the bottom is crystalline silicon, which has a perfect silicon lattice that I just showed you. Now you can assert that clearly at the interface, some shenanigans must happen because this is amorphous, this is crystalline. Clearly, there must be defects at the interface. And there could be some defects on the interface in terms of structural defects, but when you actually go and measure them electronically, we actually don't find any. And this is one of the reasons why silicon dioxide interface is probably the most important commercial interface in the world. All right, sorry, somebody walked into the office. Okay, next bit. The next way in which we deposit things is physical vapor deposition. Okay, so as the name suggests, physical vapor deposition is where we don't do the chemical bit, the chemistry bit of chemical vapor deposition. The idea here is that the material that you're trying to deposit already exists in the form that you wish to deposit. So if you're depositing tungsten or some metal or aluminum, aluminum already exists as aluminum, tungsten already exists as tungsten, next. Actually, tungsten, I take that back. How do you then move the material from your source to your substrate? You physically transport it. The easiest thing you can do is put the whole thing inside a vacuum chamber and apply some heat. And because of the heat, the source will start subliming or evaporating. And that evaporation or sublimed vapor will go and condense on top of your wafer. Very similar to how if you are boiling water and you keep a lid on top, the water will boil and coat the undersides of your lid. This technique is not used to make too many device quality films where devices are made, but it's routinely used to deposit stuff like metals or stuff like dielectric films that or optical quality films. This is actually also the technique that they use to, for example, coat the. Um, can you see my cursor, Seema?
No, sir.
तो I wonder
Try
how do
again.
नहीं मतलब वो basically there was a I had it but now I can't seem to find it. Interesting. What happened? Okay, maybe I just went full screen too much. Is that the problem? Did you change the form factor by any chance? Like it was a little less zoomed in. Did you make it more zoomed in?
No, sir. I did not do anything. Thank you, here.
Yeah, this is a weird problem. Um, just 1 minute, guys. Sorry. Okay. More options. Okay, let me just try again. Yeah. Let me just share again. Maybe that's
Sure.
easier. No, no, wrong.
See the screen.
All right. Back, I think. Okay.
Can see the cursor. Yeah.
Thank you. All right. So, metals and so in fact, if you have ever had fake gold on watch or seen a fake gold watch, or if you have seen anti-reflection coatings that are coated on top of spectacles that you wear, like the anti-glare things, those are all deposited by physical vapor deposition. Of course, in semiconductor, it's slightly more complicated and expensive. The easiest way to do this is to actually thermal evaporation. It's such an easy and old technology that actually it is not used in semiconductors, but it's very easy to understand. The basic idea is that you take two electrical connectors and you put a metal filament in the middle and you pass a lot of current through it. That metal filament basically becomes red hot. And if you have any metal on top of that filament, that metal will then evaporate out and condense on top of your wafer. We routinely use this in R&D, but this is such an old school way. Nobody does this in actual manufacturing. One of the reasons they stopped using this in actual manufacturing was the filament that they used to be tungsten or molybdenum. And all these metals during their refining process use sodium, potassium, these kind of alkali metals. And those alkali metals caused contamination in the silicon wafer. So silicon industry slowly moved away. Silicon industry is really sensitive to ppm levels of problems. So what do they actually use these days? And by the way, those of you who are keeping track, where have you seen this before? Well, this is exactly what a bulb looks like, right? This is what a bulb is. It's an evacuated chamber where there is a filament where you flow current and it glows red hot. Okay. The more modern technology is actually using sputtering. The basic idea of sputtering is to use plasma. So you have an anode, you have a cathode. These are at very high voltages. The substrate is kept on anode. Actually, maybe after this, I'll take a question. The substrate is kept on anode. The target, that the material that you wish to deposit, that is set on the cathode. Now, if you put high enough voltage on it, ultimately the gas inside will ionize. That gas typically is argon for two reasons. Number one, argon is heavy. That becomes important in a minute. And the other reason, it's inert, so it doesn't contaminate the material that trying to deposit. As the gas ionizes, it forms argon plus ions and electrons. Electrons will go to the positive charged anode. The argon plus ions will go towards the negatively charged cathode. But they will do this with some speed. So the argon ions basically are literally bombarding the surface of your target. Because of this bombardment, metal particles or whatever that you're trying to deposit, its particles are ejected out into the space and they basically form a vapor. And that vapor goes and gets condensed on top of the substrate. So it is the physical bombardment of argon ions that is actually causing the deposition, and that is what sputtering is. Where have you seen this kind of technology before? Well, this is exactly what happens inside a cathode ray tube or CFL lamp or a fluorescent tube. Basically, electrode, high voltage, pass current, and then you get a glow of the plasma that is formed by the inert gas inside. Okay. All right, I can take a few questions. Seema, you want to select?
This
Maybe I can go through it. Not too many questions. Okay. Anyways, why does it matter that argon is heavy? Because sputtering, right? So you are bombarding the surface. Heavier you bombard, the more efficient you are. This process method is better for coating substrate CVD or PVD. In terms of efficiency, it depends on how you define efficiency. But in terms of cost, which is one measure of efficiency, PVD is cheaper. Professor, earlier you said BL is considered to be dirtier. Does that simply mean it's contamination tolerant? No, it's that simply means that once you introduce metal, there are a bunch of things you are not allowed to do. For example, you're not allowed to heat the wafer. Now, why are you not allowed to heat the wafer beyond a certain temperature once the metal is there? For that, you need to understand diffusion. So let's park that later. But basically, once a metal touches wafer, diffusion becomes an issue. And to prevent diffusion, you never heat the wafer beyond certain temperatures. So you mentioned CVD, PVD for deposition. When to use which one? When to use which one is a much more complicated question. You will not get an answer for that easily in this short a time frame. Um, I mean, these are questions that are dealt with by very careful studies. The thumb rule is CVD is more expensive, uh, more challenging, more um, complicated, but gives better performance. PVD is simpler, cheaper, but gives less performance. But that's the thumb rule. There are versions of CVD and PVD. They are not just one technique, and details matter. Um, can we use eco-friendly or biodegradable substrate for low-cost IoT devices? Maybe. You have to understand silicon is remarkably A, good, B, cheap, C, biodegradable, and D, available. Um, you don't use that much real estate. You don't use that much silicon wafers to sort of justify completely changing the material. People have tried replacing silicon. They have really tried. Nobody has succeeded. Both wafers look different in the picture. The one that has say P or N, but what does it completely say? We will get into the weeds of what a wafer does. We will have a whole lecture on it. Right now, just look at the forest view. Don't get stuck in the weeds. Um, what is the ongoing trend for smaller and smaller IC chips, and how can we go? Uh, people have been predicting the ends of Moore's law and end of scaling for a very long time. Some people say scaling already ended, but progress in other things has ensured that we keep coming out with new chips every 2.5 years. Why silicon preferred IC over germanium? As I said, silicon dioxide interface. If we keep on making smaller and smaller, then what will happen when we reach physical limits? Like, because we are not just keeping making smaller and smaller, right? What we do is we also make systemic improvements. We also make design improvements. From planar MOSFETs, we became FinFETs. Now we are making GAA FETs. So improvements can come in very different forms. It's not just about scaling anymore. Okay, 329. One more, two more questions, then I'll move on. Is India developing zero-waste foundry technology like TSMC? India doesn't have a foundry. Let us first import technology and first do a lot of waste 28 nanometer technology that actually works. Once we have a fab running, then we improve it. First, we need to walk before we can run. What are environmental hazards of semiconductor foundries? We will discuss this in the next lecture. How do deposition techniques like CVD, PVD, ALD differ in terms of accuracy and application? Again, something that we shall discuss. This is not an easy answer to give very simply. Why can't we bring all the processes such as design, manufacturing, ATM under one roof? That is what Intel tried to do. Short answer is Intel's experience has taught everyone that they are probably better off doing things separately, but doing them well. This is not a question unique to semiconductors. Everybody asks the question, should we specialize or should we vertically integrate? Intel chose to vertically integrate, TSMC, Amkor, NVIDIA chose to specialize. Currently, as things stand, it looks like specialists are doing better. But if you go back and look at 20 years ago, Intel was doing better. So I don't think there is a perfect answer for this. It's just that given the correct state of being, specialists are winning. Maybe 10 years from today, The answer will be different. I don't think these are set in stone. Okay, let's keep going then. I think I have largely taken
Can we use any
questions.
inert gas other than air?
Yes, we will discuss that again. You can use in most inert gases. Krypton, xenon. It's just that argon is the heavier. The only thing heavier than argon is xenon, but xenon is way more expensive. Industry uses xenon. We don't.
The process which method is better for coating the substrate CVD or PVD in terms of efficiency?
That we discuss. Efficiency depends on what? Cost-wise PVD. Performance CVD. Which metal is most suitable in PVD method? Again, depends on your application. PVD doesn't decide what metal to deposit. You decide with metal to deposit and you figure out how to do it with PVD. Okay, take it. Let's keep going. I'll take more questions at the end. All right. Next comes to the patterning, right? So we have taken a wafer, we have done a deposition. Now we want to create a pattern. Now, the general idea of creating a pattern is you don't directly create the pattern on the deposited film. What you do is you first deposit something called a mask layer. Create the pattern on the mask layer and then do etching to remove the parts of the deposited layer that you don't need. So those of you who have ever done some craft like batik, or you have done a craft like, or if you ever know how old school photo negative films used to be made, this is essentially the same technology. Okay, this idea that you protect a little bit of the portion, do some process on it, and then remove the protective film is kind of a standard thing that is used in that humans have been using in crafts for forever. What makes this interesting is to the level at which we have specialized it and the level to which how small we can go. Okay, so let's first talk about what the process is. So step by step. So supposing you are depositing silicon dioxide on top of a wafer and you wish to now create a mask on top of this. So what you would do is you would first coat it with a chemical, a specialty chemical. The chemical is called photoresist. As the name suggests, its property sort of changes because of photo light. Okay. Then you take this photoresist coated wafer and you expose it to light. But you expose it to light through a mask. Now this mask has all the all the design that you wish to create, the pattern that you wish to create. So when you shine light from the backside, some part of this mask is opaque. It's black, so the light doesn't go through. Some part of the mask is transparent, so the light can go through. So depending upon what design you have on your mask, it's negative or positive, depends on how you look at it, gets created on top of the photoresist. A shadow gets created. Because of that shadow, properties of the photoresist change. Specifically, its solubility changes. So some part of the photoresist that is exposed can become more soluble, sometimes it becomes less soluble. That depends on the details. But overall, what you are doing is you are getting some contrast. That between exposed and unexposed photoresist, you should have some contrast in solubility. Once you have that contrast in solubility, then you go and put it in a developer solution. The developer solution will basically dissolve the stuff that is easy to dissolve, does not dissolve anything else. And what you have done is you have successfully created the pattern onto the photoresist. So now the pattern has gone from your mask onto your photoresist. And then this will go for the next bit of processing where etchants will come in and etch all the silicon dioxide that is exposed. So that comes later. This process, again, is not something that is very new. I mean, humans have been doing some version of this for a while. Most recently, this is exactly what the old school photo film before digital cameras became a thing, that they were. They basically were just developers. They were just photo films that were being developed. You had to go to a shop, a photography shop. They would take your film. They would go in a dark room and they would basically do processing inside. And that is exactly what this is. In fact, early companies that started doing lithography were all photography companies: Nikon, Kodak, Fujifilm, etc. Okay. This is what a mask typically looks like. So this mask is essentially a glass sheet, if not glass, then at least use silica quartz. And in there, you have created a pattern with a metal. Okay. So this dark area that you actually see, these are metal patterns. Okay, they're reflective. And they just look dark in this picture. And you can actually see that there are individual devices here, right? So So the metal basically is the reflective surface which does not allow the light. It's an opaque area. Wherever the metal is not there is a transparent area. These are called masks. These masks are made in have to be made for every new IC that we wish to make. In fact, that is what that is where the process first starts. So when, for example, Intel or NVIDIA make their new chip, what they first have to do is convert their blueprint, their design, into a set of masks, and the mask plates are written, and then using those mask plates, we start writing things on top of the wafer. Now, those of you who are following this very closely will ask a chicken and an egg question. They will say, great, what you basically said is first create a pattern on the mask and then transfer it to the wafer, but then how do you get the pattern onto the mask in the first place? कौन पहले आया? Chicken or anda? Short answer is mask is made through a separate method. So what actually we do is there's things called mask writers. Now, what I'm showing you is the simplest of it, something we have in our lab. The commercial mask writers are much more complicated, but the basic idea remains the same. The basic idea is you have a laser, a very sharply focused laser, and you are writing the pattern on top of your mask pixel by pixel. So you're literally turning the laser on, off, on, off, on, off, and you're converting an image into a pattern on top of the wafer. Sorry, on top of your mask. Now, if you could directly write on the mask, then why do you need a mask in the first place, right? I mean, you should then just go directly and write on top of the wafer. The short answer is the reason we don't do that is speed. You see, when you do this lithography process, this is a parallel process. The whole wafer gets written in one shot, which means that we can do hundreds of wafers an hour. However, when we write pixel by pixel like this, it's a remarkably slow process. I don't know exact details, but I have been told that a typical Intel mask set will, for example, take months to write. So it takes months to sort of get everything ready enough that you can actually write this pixel by pixel. So we don't have that much time when we're doing the wafers, which is why we use parallel lithography process for processing wafers, but we make masks using mask writers. Okay. This is what the exposure system looks like. Basically, this is our aligner. This is again what would be in an R&D setup. Commercial systems are much more complicated. But the basic idea is there's a UV light source, typically ultraviolet. Now, why ultraviolet and not red? We will discuss this. This is related to resolution. Then there is some lensing, which sort of collimates that light. This is your mask. This has the pattern on it. Then there is some other projection lens, much like a microscope. So you shine light, the mask creates the shadow, and that shadow gets written on top of your wafer. On top of this, we are calling this aligner. So that maybe requires some description. So why aligner? So the reason is you don't just do this once. You create a pattern once, then you create a pattern a second time, then you create a pattern a third time. Every time you create a pattern, you actually want that pattern to be aligned with how the first pattern was aligned. So that overlay is not arbitrary. It has to be slightly precise. So these aligners do two things. They of course expose, but they also allow you to align your mask with the older pattern that has already been written on top of the mask. When done well, lithography works extremely well. With photons, we can easily write 1 micron type features. In our lab, commercial fabs can do much better. Commercial fabs with steppers and all can easily write 250 nanometer lines. With some advanced techniques like SADP, multiple exposure, etc., people can write sub 50 nanometer features. For really in small scale features like 10 nanometer features or 20 nanometer features, sometimes people use e-beam lithography. Just like electron microscopes are more powerful than optical microscope, electron lithography can actually write smaller features than optical lithography. What happens, why this is the case, we will discuss when we discuss lithography. Okay. I can take a few more questions at this point. Let's go to new post. Maskless versus mask methods in lithography, is one better than the other? I mean, it's just one is slower, one is faster, but one is cheaper. The usual optimization problem of any manufacturing. There's a concept of negative and positive mask. Does that have to do with the fact that pattern is inverted? Exactly. So It depends on the tone of the resist. It also depends upon the pattern on the wafer. Also, directly using mask writer in the wafer, won't it somehow can also damage the wafer? It can, so you have to be careful. I mean, these are details that you have to, not that hard to do this. Mask from Oscilla cost too much. Is it possible to put? Yes, we can write masks if you want them to be written. When using chrome masks, won't UV light make extra reflection? Yes, so all of those details have to be handled. Anti-reflection coatings are to be added. There are many details with it. It's not trivial. And by the way, which leads to the next point I wish to make. Physics people are heavily used in optics, or people with experience in optics and people with experience with cameras and etc., lasers, etc., are heavily used in semiconductor manufacturing. How do we build multi-layered ICs when a particular photoresist layer is already staying on top? No, we remove it after we are done. SOI is a mask analogical to Gerber from PCB design. You can think of it that way. In fact, Gerber files is one of the formats we use for writing masks. What is the working of photoresist? Explain that. Are we adding mask for ion implantation? Yes, you can. That's one way to pattern ion implantation. How thermal evaporation and impurities in PVD details we will come to later. All right, moving on. Once you have done your mask, you have a photoresist, then invariably you want to remove your material from some places. In this case, I'm trying to remove this red region in the middle. So what you would do is you will basically take this patterned wafer and dunk it in a solution which attacks the material that you wish to remove. For example, if you're trying to remove silicon dioxide, you would dunk it in a solution that etches silicon dioxide. A common example would be hydrofluoric acid. But then this can be generalized. Any material you wish to pattern, you need to find an etchant. Usually these are bases, these are acids, they are combination of acids and oxidizers. For each new material that you wish to etch, there is a new recipe that you have to create. The things that are under your control are what concentration you're using, how long you're exposing it for, and those kind of things decide what is the etching rate, what is the selectivity, etc., etc. Now, these are details we will discuss later, so I will just park them for now. Okay. What happens to the byproducts? The byproducts must necessarily be soluble. In fact, that is how this chemistry is defined. For example, if you're trying to etch silver and you do it with hydrochloric acid, sure, silver will be attacked by hydrochloric acid, but then it will form silver chloride. Silver chloride is a precipitate. It does not go anywhere. So that is not a good etching solution. That is not a good etching recipe. Modern device making has largely moved away from wet processing to dry processing because wet processing has certain challenges. Problem number one is not as repeatable as you wish it to be. It's very simple and cheap, but it's not repeatable. Then surface tension always plays spoil sport. If you are making very small features, MEMS devices, oftentimes you are fighting battles of feature collapse, surface tension, etc., etc. There are ways of getting around it with critical point drying and this and that, but it's hard. Much more interesting or much more used these days is the idea of dry etching. I'm being a little simple here, but to a first order, this is complete reverse of sputtering. The basic idea remains the same. There's anode, cathode, there's a plasma, create the plasma. But this time, instead of bombarding the target and ejecting material out, you bombard the wafer and remove the material. The one detail that is very different is it's not just a mechanical process. It's not just you're bombarding argon ions. You can also bombard chemical ions, which have which react with the material that you're trying to etch. So it is not just a physical bombardment process. It's also a chemical reaction process. And this is one of the reasons why people who understand plasma, people who understand plasma chemistry, model plasma chemistry, people who understand what am I looking for? Radicals, people who understand how to characterize the active species inside plasma, etc., are heavily needed in semiconductor technology. When done right, you can make very interesting features. So whatever you have created in the masking layer gets transferred to silicon. You can make micro needles, you can make RF devices, you can make resonators, You make narrow holes that go very deep. These are called through silicon vias, etc., etc., etc. Okay. Which brings me to the final bit, which is process integration. What the hell is process integration? Process integration is, look, what we have discussed till now is called unit process. Another way to think about the mechanical analog is, I know how to do lathe, I know how to do drill, I know how to do milling machine. I just know each of these individual machines. But that does not make a product. In order to make a product, you need to use each of these methods in a certain order, in a certain fashion, with a certain design. And when you do that all, then you will get with a working system that works at the end of the day. Semiconductor is no different. So somebody has to sit down. A device engineer has created a device or something that they wish to make. Somebody has to sit down and figure out how to actually fabricate that thing inside a system using the various unit processes we have at our disposal. Sometimes for established technologies where everything has been figured out, that is just a mechanical method, mechanical work where we already know what the right answers are. We just have to follow them. But sometimes it can be complicated. For example, the process integration engineer who's sitting at 2 nanometers and deciding what type of processes are needed to make the 1 nanometer device. That's an extremely hard problem. Because if you take the 2 nanometer technology and just shrink it and just run it, it will fail. Guaranteed fail. But then you look at that failure and say, okay, what failed? Okay, this process failed, that process failed, this did not work, that did not work. And then you start coming up with ways of fixing them. Okay, I'll fix this way. This I will fix this way. It's a non-trivial problem because things affect each other. It's not a straight path to what the improvements must be. Okay? Even in a mature technology where the answers are known, it's the process integration people who basically do the detective work. So for example, Tata is setting up a fab, right? I promise you the first 6 months of that fab, things will not work very well. They will have the same tools, they will have the same people, they will have the same processes. But still, because of some variation that they don't completely understand, their output will not be as high as the fab that is there in Taiwan. And this is known. This always happens. Every time a new fab is built, things don't work. It will take them 6 months, and if they are good, they'll take them 3 months to figure out what all is not working and slowly, one step by step, eliminate all the problems so that the whole thing works. That job is also of process integration. In fact, it is for this reason that process integration people are probably the most well respected and one of the most satisfying job profiles inside a fab. They also tend to be the most experienced people, the most well paid people. It's a role that you cannot sort of train for. It just comes with experience. It's not like we teach a course in process integration, but I'll be honest, unless you actually do things on the ground, right, you do not completely get the hang of it. It just is something that comes with experience. You need to fundamentally understand many things. You cannot just be an electronics engineer or material scientist. In some ways, you have to learn everything. Attention to detail matters a lot. I promise you, anything that you have not thought about, any assumption that you have made will come to bite you. So it just devil is in the detail. You don't assume anything. You have to be intimately aware of practical details. You need to understand the limitation of your process, your equipment. You have to be extremely good at communicating. I mean, you cannot just say, hey, heat the wafer at 120 degrees C and do X. How you heat the wafer? What are you planning to do? Like, there are levels to this that are kind of amazing. And that's what makes it interesting. In fact, I'll sort of end on this anecdotal note. I was talking to some industry professional who shall remain unnamed, some pretty senior CEO level person. And at that point, this was a few years ago, India Semiconductor Mission had just been launched. And I asked, do you think it will happen? Like, will India make a fab and will the fab work? And he said, you want my official answer or you want my real answer? I said, give me your real answer. So he laughed and he said, it will be a challenge. And I said, why? He said, he gave me a story. He said, I just came from the Delhi airport. According to rules, I'm not supposed to enter the airport 6 hours before 6 hours of the flight time. Like when I came, I was 8 hours before because I took an international flight. I was not supposed to get in, but I showed my boarding pass. They scanned it on the machine. The machine went red because it was 8 hours and not 6 hours. And he said, but the guy looked at me and said, yeah, कोई बात नहीं है, अंदर आ जाओ. And he said that is the problem because that doesn't work in semiconductor. You cannot just, there is nothing called Jugaad tech doesn't work in semiconductors. Violating rules doesn't work in semiconductors. Even if you don't understand why this is the way to do things, you have to do it that way. And he said that is a cultural context that I'm not so sure will happen in India. I guess the reason I'm telling you this story is I hope you prove him wrong. Because if you do take this as a career, then that is one of the first things you'll have to get over. Chalta hai doesn't work anymore. Like there's a reason Japanese, the Korean, and the Taiwanese are so good at it. That attention to detail really matters. All right. Overall, if you do it well, out comes a wafer that has all the chips, and we have already sort of discussed. Then you dice it into dies and then package it, and off you go. One of the interesting things about this approach, however, is that there is actually a separation of church and state that is important to understand. The whole semiconductor ecosystem has a certain modularity. There is a person out there who runs an instrument, who runs a deposition tool or an etch tool. They understand that tool very deeply. They understand the recipe that they have been given very deeply, but they don't actually need to understand at all the device that is getting made. On top of that is sitting a process integration person. They understand the integration, they understand the unit process. They may not have completely all the details of how to run the tool, but they understand the process. But they also don't need to know what the device design looks like. They just need to know the process. Then there is a device engineer who makes the device design, who does not need to know how the instrument runs, who does not need to know how it is fabricated to a first order. And on top of that is sitting a circuits person who will just take this device, who will just look at the data sheet of this device, design a circuit, and it will work without knowing how any of those three people below them did their work. And all of this sort of works because of documentation. What semiconductor industry has been very good about is documenting all of this. They have a roadmap. Okay, 3 years from today, this is what we will need. 3 years from today, equipment manufacturers will have this equipment ready. 3 years from today, chemical manufacturers will have this chemical ready, etc., etc., etc. And they have created a system that has been basically functional for the last 90 years, and that is kind of amazing. Okay, last bit. Overall, the chip process can be remarkably complicated. It will work. No, it will not work. Okay. So this is just to sort of give you one example of a certain module that has been that is to make a FinFET module. But basically, there are multiple steps. It's hard to sort of imagine how it all comes together. I don't think you will sort of get it in one shot, I guess is the point I'm trying to make. It does take some experience and some time. And even today, I don't think there is any one person, even in places like NVIDIA or TSMC, who basically understands the whole process in its complete entirety. The thing has become complex enough that all the information that we actually need is housed in multiple brains and multiple industries and multiple companies. It's not one thing anymore. All right, I will end here. Time for questions. Is wet etching usually isotropic? Yes. By using lithography or different methods of VLSI, how we create different types of components. In some ways, it's a little bit of a jump, but basically that 2D mask that you are talking about, just by making interesting shapes, you can actually create any device you want. Which one is better in terms of efficiency, wet etching or dry? Again, efficiency, what? Cost, wet etching, performance, dry etching. Can we use the sputtering instrument to etch? No, the equipment is different enough. The concept is similar. Why does the dry etching system make metal mask and insulating mask are kept and used separately? I mean, those are details that we'll have to get into before I can answer it. Why X-ray is not used widely in lithography? Expensive. Throughput is low. UV, EUV was a pretty big jump, and there's only one company in the world who has figured it out. What do you mean by wet etching is not repeatable? Are you saying we can't stack it? No, we cannot. If we run 1 million wafers, what is the standard deviation that we get in the performance of the etching? If the standard deviation is not narrow enough, then that's considered not repeatable enough. This chemical etching process, the HF only. No, there are many etchants. I just gave an example. Can you please tell me what is photoresist? I don't get it. Photoresist is just somebody whose property, whose solubility property changes depending upon how much light exposure they get. So it's a specialized resin whose solubility can be changed with light exposure. Is there scope in semiconductor industry for metal? What you're joking? Deposition and all is completely material science, people. A lot. Materials are the core issue. So in general, all the processes used in semiconductor industry aren't new. They've just been made more efficient and scalable. That is all technology. Um, Revolutions don't work. Evolutions do. I have heard that masks are basically made by making a base scale mask traditionally and then scale it. That is true. Typically, masks have a 1:x ratio of reduction, but that is not what makes it, I guess, easy or simple. The issue of resolution is still there. You cannot cheat diffraction. When Shankar talks about it, you will understand what I mean. UV light is used in lithography, why X-ray was not used. Expensive. IBM tried, could not make the economics work. Does the refractive index of the photoresist or air gap influence? Yes, absolutely. That's why optics and physics people are needed. So is there masking from one side? No, you can do double-sided, but most commercial technologies don't need double-sided. Some do. Whether the mask in case of EBL is also made by mask writer? Yes, E-beam mask writers exist. Maskless versus masked method in lithography. Yeah, okay. This is the same thing. Go to new post one more time. What challenge will arise in process integration when stacking multiple layers in 3D chips? Hundreds of processes. Other than process, there are other problems that arise. For example, heating becomes worse. Signal integrity becomes a problem. Reliability becomes a problem. Stress, delamination, compatibility issues. 3D integration is hard. How ion beam technology is used? Ion beam is usually not used. R&D people use it, but not in mass manufacturing. It's too slow. In general, all the process used in semiconductor industries aren't okay. That is a question I've already dealt with. Why is the mask made of chrome? Yeah, it's a hard material, does not oxidize, reliable, just works. But very bluntly speaking, I don't know if there's a deeper answer. All right, that's it. So, Tima, another 5-minute break.
Yes, sir. We should.
All right, thank you.
We'll resume at 4:04. Hi, we are requesting again and again, please do not raise the hand. If you have any questions, please put it in the Q&A toolbar. Raising hand and then we are dropping out, it creates a disturbance to the speaker out here. Please understand.
Okay, Seema, we definitely are behind. I just sort of realized I bungled up the timing. Okay.
We can get it started, sir, then.
Chalo, then let's get started. Okay. Next is wafer cleaning, right? Chalo. Okay. Cool. Hopefully I'm visible. Let's get started. Okay,
Yeah, it's
so
visible.
let's talk about clean room. So I'll flip a few slides, but let's get the main point across. So what is a clean room? All right. Basic idea of a clean room is that it's a controlled atmosphere where we need to get particle count down. Why particles have to be down is kind of obvious. We are trying to make things at the nano scale. Any particle that falls that is of the similar size will create problems for us in terms of in registration features. The way we keep the clean room clean is that it's continuously continually run with clean and purified air. So there is a fab, and in that there are HEPA filters on the top, and there are holes in the bottom, and air is sort of circulated continuously from top to bottom through the material. Okay, so through the clean room, sorry. MAH stands for basically air handling units, and so the air handling units are basically pushing the air in. These filters are continuously purifying it, and this downward flow of air is basically what keeps the clean room clean, because any particle that is gets created is pushed down into the subfab and does not circulate in the room. Go back to this image that I showed you earlier of the Intel fab. You can actually see the holes in the floor through which the air will go. You can actually see the tools. And you'll also notice how few people are there. That's by design, because the fewer the people, the fewer the particles, the cleaner the clean room. The second thing I want to highlight is look at the top. Those rails that you see, these are robots, automated material handling system, AHMS. These robots basically control these scoops. These scoops are front opening unified pod, basically a dabba which has wafers. You can see wafers inside. These remain continuously sealed, and that also protects the wafers from any particles that are forming. It's not only the clean room clean, but the FOOP itself is clean inside. The reason these for robots are important is because most modern fabs are completely automated. It's not humans are moving things from one place to the other. It's only robots doing. In fact, there's remote operation, meaning there are people sitting in Bangalore who are controlling fabs that are running in Malaysia. For them, it's like a video game. But in reality, there are robots in the back end that are actually moving things back and forth. Because lithography has photoresist, which is light sensitive, the lithography room has to be extra sensitive to light. So typically these are yellow rooms or dark rooms. They have even fewer people, and mostly things happen automatically. This is probably the most expensive and critical part of a clean room, the litho area. Overall, actual clean room is essentially a very large instrument in its own right, or very large equipment in its own right. It has safety systems. It has ways of detecting smoke. It has ways of detecting dangerous gases. You need ultra pure water. You need compressed dry air. You need process cooling water. You need exhaust for taking the waste gases out. You need exhaust for taking chemical vapors away. You need to make sure the wafers and the other things that you are managing are the same thing happened. Oh, take control. Somehow somebody is taking control. Oh, okay, that is the problem. Very interesting. Okay. Then what I was saying, then you have to make sure those vapors that you are sort of dumping taking out from the clean room have to be scrubbed. You cannot just let out toxic gases into the environment, etc. Overall, people have to reduce both particulate contamination as well as chemical contamination. So these are some of the examples of problems that can happen. Okay, so if you don't remove the particle, then basically between two metal electrodes there is some junk sitting, which can reduce performance. You have created a pattern, but that pattern has a defect because there was a particle sitting there, etc. Moving on. Typically, clean rooms have a certain class that basically represents how many particles there are in a certain cubic volume. So it used to be class 110. These were American standards, so they were in per feet. The modern standards are ISO standards. Normally, the lower the number, the cleaner the clean room. So class 100 is more clean than class 1000, etc., etc. Modern fabs can routinely have class 1 clean rooms. Our fab in an academic setting is class 100. The biggest problem inside a clean room is a human. No matter what you do inside the clean room, you produce particles. And this is why you never enter the clean room without a bunny suit, because the bunny suit is what protects. For specialty cases, for example, in this case, this IBM engineer is handling a mask. They have even further protection to separate you from the mask so that particles don't fall on top of the mask. It is these kind of details that make semiconductor manufacturing both challenging and expensive. The next bit I'll talk a little bit about is chemical contamination. So the reason chemical contamination is pernicious is that it sometimes does not change performance. All it does is it adds variability to it. So this is a very good example from a paper. Normally, if you make a million devices, all the devices should basically be on top of each other. Because if they are all exactly the same, a circuit designer can create a circuit and the circuit will work as designed. When you start using chemicals that have slight contamination, then what happens is every now and then some devices have a different characteristic than the first. So that adds variability to the system. It's not like all devices are failing. Is that some devices are performing slightly poorly. And because of that variability, just look at this curve and this curve, right? I mean, this is so much more variability. This you get even if you add just 5 into 10 to the power 11 molecules per centimeter square. I hope you sort of appreciate how small a number this is. This is 1 in a million clean surface. So just 1 in a million particles can basically, or chemical contamination can basically kill the repeatability of your process, let alone if that number is high. So this is why chemical contamination is very important. One of the basic ways in which we reduce chemical contamination is by just having the purest water you can find. So the water we used is called deionized water. This is not distilled water. This is better than that. This is not, I don't know. This is not RO purified water. It is much better than that. In fact, it is so much purified that it stops being a conductor of electricity. It becomes an insulator. In fact, that's how we measure it. We basically measure its resistivity, and resistivity needs to be better than 18 mega ohms centimeter. Making 1 liter of DI water is nearly as expensive as a petrol. So it's very expensive. And so you treat it with care. The second thing we do is we use something called CMOS grade chemicals. These are state-of-the-art cleanliness grades. These are the purest grades you can buy in the market. You don't buy anything else. In order to be a semiconductor grade, manufacturers have to follow extremely tough norms. Okay, if I'm selling you ammonium hydroxide, the trace contamination of all these other elements need to be in parts per billion or parts per trillion. Semiconductor manufacturers routinely are able to achieve levels that are closer to parts per parts per trillion in terms of contamination. Okay. And last bit is we use ultra high purity gases, oftentimes with inline filters to purify them even more. Most of these are at least 6N pure, which is 99.9999%. So a combination of ultra pure water, ultra pure chemicals, and ultra pure gases is needed to make semiconductor manufacturing happen. Now, one of the challenges of dealing with semiconductors is safety. Okay, many of the things that we use in semiconductors commonly, even our fabs, are toxic, and if we allow it, they will kill you. We use chemicals, we use gases. Some of our gases are so toxic that you should never smell them. We have radiation hazards, we use lasers, we use high magnetic fields, we use high electric fields, high voltage. We have cryogenic hazards, sometimes use liquid nitrogen. Of course, fire hazard, we use extremely high amounts of power. ISE has 42 departments. CeNSE is one of those 42 departments, and we use 1/4 of the electricity requirement of ISE. That is how intensive electricity use we have. All of these effluents create environmental hazards and, of course, electrical hazards. So all of these need to be dealt with. I cannot give you too much of a safety sort of an overview because, frankly speaking, that takes longer. But in general, the idea is you always have wear PPE. Semiconductors, the discipline to wear PPE is extremely important. You will probably not get a job if you cannot, or you cannot keep a job in semiconductor technology if you cannot keep PPE discipline. There are rules of transporting chemicals, segregating chemicals, disposing chemicals. It's not like you throw things down the drain. You have to be much more careful about it. Uh, there are ways in which you store and use cylinders. You see, these are not just simple nitrogen cylinders, even though they must be respected. We actually use chemicals that are far more dangerous. Okay. So, for example, one of the things we do is we use hydrogen. Now, hydrogen is one of our low risk gases. Okay. Hydrogen on its own is considered very dangerous. It is explosive. It takes very little energy to put it to basically trigger an explosion. Hydrogen flame is transparent, meaning that sometimes you can't even see it. It also is very light, so sort of it hides in nooks and crannies. So these are issues with hydrogen. And as I said, hydrogen is one of our simpler gases. If you actually start looking at the other gases that we use in semiconductor fabs, they are far worse. For example, things like disilane, diborane, arsine, dichlorine, chlorosilane. And these dangers are real. India actually had a fab before Taiwan ever did. In 1980s, we had a fab in Chandigarh. It was called SCL, and it burnt down. It was a silent fire, and India has not recovered. And that loss of capital and loss of investment, we could never fix. After that, Taiwan started making fabs, and today, of course, they are so far ahead of us. More than then on top of that, those are details. One of the things that we sort of very quickly realize in safety and all of these things, the things have to be very clearly documented. It's trainings and all are not verbal. It's not like I tell you how to change a cylinder or I tell you how to do this safely. Everything has to be written down and exactly followed to a T. Copy exact. Because people who don't sort of listen to these kind of problems get into trouble very quickly. We have never had a major safety incident in CeNSE, touch wood, but it's not like things don't happen. It's just that we have a system in place to make sure nothing ever gets out of control. And that's very important. Even small incidents, somebody forgot something, somebody made a discipline error, somebody forgot to close the cap of a chemical, somebody mishandled a chemical. Those things happen. But unless you police those small incidents, you're just asking for a big incident to happen. Okay, I went through this very quickly. My apologies. You will get the slides, but I think I covered most of the important bits. Any questions you have on this, I can take. What is the room temperature of a clean room? It really depends. We typically try to maintain 21 degrees plus minus 0.5. I found it interesting when you said chemical contamination can pile up and increase variability. Could you explain? Yes, I will talk about cleaning in a minute. I will show you explicit example. Wafer goes through the clean room processes one after the other. Every time you do anything to the wafer, you are giving an opportunity for contamination to build up. So unless you have ways of reducing contamination, you run into trouble. So why do we use extra purifiers even after getting a clean glass? We have to overdo things. Because some of these problems are only because they increase variability, they're very hard to pin down. Most of the day, things will work, and then a few days, things will not work. Chasing, finding exactly what is causing problems that are happening every now and then is a full-time job. So there is contamination happening, and no matter how clean the clean room is, there is bound to be to do measurements. I would not go far to say that you basically measure everything every single time, because then that just slows you down too much. But there are people whose full-time job is what is called yield analysis, who will basically look at the performance of the fab, figuring out what is causing the loss of performance or loss of wafers or appearance of defects, and then make changes to the process so that those reduce. That's a full-time job. So I work on report controlling robots, and we need ultra clean. Why not just use vacuum rooms for safer, cleaner? It's not easy to make vacuum systems. On top of that, vacuum systems oftentimes have a lot of particles because vacuum comes because you create vacuum using moving plates. I mean, we are getting into some sort of a detail here, but these things have been thought to death. Uh, the best ideas are being used. There is no need to reinvent wheels. Also, where could we get these PPTs? I think there is some version of sharing. One basic doubt, without a clean room, how is mobile or any other device? Because those are packaged devices. You never repair an IC. When you're saying you are repairing a mobile phone, what you are actually repairing is just the assembly part. Chips are rarely repaired, they're just thrown away. Okay, let's get started on the next bit. All right, so this part of the talk basically will talk about a wafer. I'll go a little bit in detail of what the wafers are, how they are made, and then how they are cleaned. Okay. So we already discussed this. Silicon is probably the most important, and the most important thing is this ultra pure. But there are other materials available. 90% is silicon, 95% is silicon, but people do use others. Common ones are silicon, germanium, silicon germanium. Now those are all group 4. Okay, if you're sort of keeping track. Then you can also do is you can keep in the average of 4 electrons in the outermost shell, but then make 3 5s, which is one of aluminum and phosphide. So aluminum phosphide, aluminum nitride, aluminum arsenide, etc. Or gallium nitride, gallium phosphide, gallium arsenide, etc. So those are called 3 5 semiconductors. You can similarly do 2 6s. So you can do zinc sulfide, zinc phosphide, zinc sulfide, zinc selenide, etc. etc. So that is the zoo of semiconductors that are typically available. Silicon is used for most applications because it's most mature, but also because it has amazing mechanical properties. It's actually a remarkably mechanically good material itself, and that is one of the reasons why we use it in MEMS so much. Gallium arsenide to a first order is used for all optoelectronic applications and high-speed applications. So optoelectronics means all your red and green LEDs are gallium arsenide. All your old school radars were gallium arsenide. All your high-speed communication chips inside your mobile phones are probably gallium arsenide. Okay. However, that gallium arsenide has not been able to replace silicon in traditional logic and memory type of applications. Okay. There are other materials which are used much less often. For example, sapphire is used for several applications like RF, etc. Silicon carbide has recently been started to be used for power electronic applications. Gallium nitride is used for LEDs and power electronics applications. But those markets, compared to silicon at least, are far smaller, but important nevertheless. Okay. How is silicon made? So silicon is made from sand. That's kind of obvious or simple. The trick is that it's not just made from any sand. To my knowledge, most of the sand that is used to make silicon wafers all over the world actually comes from America in one village, someplace in North Carolina, which apparently supplies most of the sand that is used for making silicon wafers. What you do is you take your sand and then you use the submerged arc furnace to electrolytically refine the silicon dioxide to silicon. The silicon that comes out is nearly 98% pure. It's called metallurgical grade silicon. This is not clean enough for semiconductor application, but this is a good starting point. This thing has nearly has like hundreds of ppms worth of contamination. This thing is refined by something called a Siemens process. The basic idea of the Siemens process is this is a fractional distillation system. So if you are a chemical engineer, you probably are noticing this. I know there is one very big company that is actually setting a very big Siemens plant in India. So if you're looking for jobs, look for it. So basically what they do is they take the silicon, convert it into trichlorosilane. Trichlorosilane is a liquid. They distill that liquid in distillation columns to purify it, and then deposit it in a chemical vapor deposition process into these chunks, okay, in a reactor basically. So you convert silicon to trichlorosilane, and from trichlorosilane purify it, and then again deposit it back to form silicon. It's called a Siemens process. And this is how you get to what is called polysilicon. So the polysilicon basically looks like this. It's basically chunks of silicon that have been ultra purified. By this time after the Siemens process, this thing is already 99.999% pure. There is no further metallurgical process by which we can refine it any further. The way we refine it further is we actually make wafers out of it using a method called Czochralski method. It's a crystal growth method. Now, those of you who are from materials, this is not new to you, but those who are from other disciplines would sort of appreciate. Whenever we take a material and create a crystal out of it, there is something called zone refining that happens. It takes a little bit to explain what zone refining is, but basically the idea is that while growing a crystal, we purify the material as we are growing the crystal. So the process of growing the crystal itself purifies it further. So, so that is what allows us to go from this 5N purity to the 10N purity that I talked about before. Okay. Now the way they make these is they basically melt it up and slowly pull out a single crystal ingot. So this is a polycrystalline material. It doesn't have any specific orientation. The lattice grains are all over the place. This is a single crystal material, ultra pure, usually weighs several tons. And then they take this ingot and do further processing to make the wafer. Okay. The reason the wafers are circular is because these ingots come out circular. They come out cylindrical. Another common way of making ingots is called float zone method. Typically, the float zone method is more expensive. The idea of the float zone method is, again, you melt and recast, but the melting and the recasting details are slightly different. In this case, the silicon doesn't touch anything. So that is because of that, it remains purer or cleaner. But anyways, that's a detail. Overall, float zone gives you cleaner purity material. This is probably gives us the best quality material there is. However, it is more expensive than the CC material. So you only use float zone when you really need it. Most commercial common use silicon that you have seen is all CZ silicon, the class B silicon. Once you have your ingot, then you cut the ingot. You essentially put it in a lathe machine and shape it. You get it to the correct diameter. You give a polish to it, and then you take this ingot and then you cut it with a wire saw. Typically, these are diamond wire saws that cut it into these wafers that you see. Now, these wafers are not ready yet because they still have all the saw marks and all the roughness from the previous processing. So then people do etching and polishing to make them smooth and shiny, and that is what leads to a wafer that you can actually use. So all of this process, by the way, happens not in a fab. This all happens behind the fab. So a fab basically purchases a wafer, but by the time it gets a wafer, this all has already been done by companies that make wafers. Okay. Okay. Any quick questions? Can we use direct silicon in hemp for RF applications? Yes, not in RF applications. Silicon is not a very good RF material. There's too much loss, but for power applications, people are trying that. To my knowledge, for RF applications, people tend to use sapphire, not silicon, but I could be wrong. I'm not an expert. So semiconductor manufacturing methods, which do you need in next group? Is it a topic of research? Yes, but in India, I mean, for example, crystal growth happens at very few places. Some of these are topics of research, but I would call it more developmental research that happens in industry labs, not necessarily R&D in academic settings. Any other questions? Where manufacturers are manufactured? Many places. China is by far the largest manufacturer. It used to be Germany was pretty big in it. The name Siemens sort of should tell you that Germany was big in it at some point. All right, let's move on. Overall, these are the specifications that you can basically, you have to give when you buy a wafer. So you have to specify the size. Most modern manufacturing, large scale manufacturing happens in 12 inches. So these are this big wafers. 14 inch was an experimental size that did not find traction. So then it fell through. 8 inch is an older technology. Some manufacturing still happens in 6 inch. Below that is essentially only R&D. Like nobody does serious work anymore. Most serious silicon work happens at 12 inch. You can get wafers with different orientations. 100 is by far the most important, simply because modern CMOS logic and processing technology requires 100 wafer. The very process of growing the wafer actually makes sure that the front of the wafer, which is this part of the wafer, is always more front of the ingot, sorry, not wafer. The front of the ingot is always more pure than the back of the ingot. Now that's a consequence of zone refining. Without getting into details, I cannot explain it. Just take my word for it. So because of that, you actually get different grades, right? The purest part of the ingot is sold at a different cost. That's called prime grade. The dirtiest part of the ingot is sold as mechanical grade, etc., etc. Then you can, of course, specify which method you use. You can specify thickness. You can specify what conductivity you have, because during the growth of the crystal itself, they can add dopants. We will discuss what dopants are later, etc. Okay, so those are some of the things you can specify in modern day manufacturing. So then you have your wafer, this ultra clean, precious wafer that has had so much work done to it before it gets to you. Then what do? You start processing it. So processing requires lithography, which is a wet chemical process. Processing requires etching, which can be wet or dry. Processing also requires depth. Every time you interact with the wafer, you introduce either particles, or you leave behind chemical residue, or you create metal ions or anions on the surface. Okay. This was the issue of contamination, sort of stacking up that I was talking about. You start with a clean wafer and it has no detectable particles on it. You do your silicon epitaxy, and just because you did some deposition step on top, you would now detect some number of particles. Then you do some other deposition and you get some more particles, and then you go and do your ion implantation, which is a form of doping, and suddenly it jumps by an order of magnitude. And then you do some more processing and it jumps by another order of magnitude. All of this basically is to say that this, unless you figure out a way to arrest this will kill your device run very, very quickly. So what people came up with, they basically came up with cleaning methodologies. Methodologies that you can introduce before critical steps so that you can reduce the contamination on the wafer back to its earlier levels. So that's what the goal of a cleaning methodology is. Okay, you basically want to reduce the contamination. Now, different contaminations require different sort of cleaning, and there is no one size fits for all. And you basically have to just be a practitioner to sort of know which one to choose. There is a certain method in the madness that comes with experience. Overall, there are certain things that you do for particulate contamination. Then there are certain things you do for metallic contamination. So metallic in this case refers to alkali metals and heavy metals. And finally, there are some things you do for other types of chemical contamination, like organic contamination, dopants, bases, or acids that you leave behind, etc., etc., etc. Okay. Okay. Normally, these are some of the chemistries that are used, and I actually don't expect you to sit down and sort of understand what these chemistries are in any detail. I will get you the gist of it. So what is the gist of it? Let's take one as an example and go through it in some detail. So let's take RCA clean. This RCA refers to Radio Corporation of America, which at some point used to do some semiconductor processing. They came up with this method. Most of the cleaning methods that we actually use are some variation of RCA, or at least if you understand RCA, you will understand those as well. So what's the RCA clean? You basically have SC1, which basically is a base and an oxidizer. You have SC2 step, which follows the SC1 step. That has an acid and an oxidizer. And then you have a hydrofluoric acid step that removes silicon dioxide. Okay, now let me get into this a little bit more detail. The first is called SC1. Here, what you basically take is you take ammonium hydroxide, DI water, and peroxide. So hydrogen peroxide, DI water, and ammonium hydroxide in certain ratio, 1:1:5 is common. You heat it up to 48 degrees C for 10-15 minutes. Now, what is happening? First thing is, there are certain metals that are more soluble in a basic solution than they are in an acidic solution. So those become soluble. Then what happens? Then there are certain metals which are not soluble, for example, silver chloride. However, they are soluble if you can make a complex out of it. And this ammonium hydroxide was not used carelessly. Ammonium hydroxide has ammonia, which is a ligand, and that forms complexes. So that complex formation creates this soluble complex, which allows you to dissolve silver, which otherwise is very hard to dissolve. Lastly, lastly, this basically has ammonium hydroxide ion, and that sort of helps in cleaning the wafer, very similar to how choline solution is used to clean the mirror on your to clean glass windows. Okay, it's a basic solution that basically helps clean the surface. So it dissolves away organic junk and organic grime on the surface. What does SC2 do? SC2 is the same solution, but instead of ammonium hydroxide, now we have hydrochloric acid. So hydrochloric acid, peroxide, and water. Now, what is this trying to accomplish? First thing first, there are many metals which are soluble in acidic solution. So this provides acidic solution to dissolve. So many chlorides, for example, are soluble. The second thing it does is if you have metals, for example, unreacted sodium, unreacted iron in the solution, then the peroxide will oxidize it so that it forms Fe+2 or Fe+3 ion or sodium plus 1 ion. And those ions are much more soluble. The metal particles themselves are not. That's the basic idea. And finally, you end with hydrofluoric acid dip. So what does hydrofluoric acid try to accomplish? Both SC1 and SC2 typically leave behind some silicon dioxide on the surface. And because they leave behind silicon dioxide on the surface, you want to etch it away, and silicon and hydrofluoric acid is a good way to etch silicon dioxide. Now, those of you who have been keeping track, in all the lecture on cleaning that I have given till now, there is not even one single iota of electronic concept. This is completely inorganic chemistry. I have sort of glossed over details, but in order to really appreciate this in full detail, you need to sort of understand reduction potentials, high oxidation potentials, stuff that you have done in 11th and 12th, but people who do chemistry for a living do in much more detail. So those are the concepts that are actually needed to create these new types of chemistries and sort of do cleaning of wafers. That's why I said sort of there is no stream of engineering that is not needed in the semiconductor fab. This is what a typical place where this cleaning is done looks like. This is called a hood. This is a hood of a research fab like ours. You can actually see the chemical is boiling away. Commercial fabs look slightly different. Commercial fabs will have these tools which are massive, where these robots sort of take the wafers and clean them. And basically what you are going to have is you're going to have series of what I would call dumps, where you will dump the wafer in one, then take it out, and dump the wafer in the other, then take it out, and keep going. Okay. Then account safety is sort of something I've already highlighted. Now let's get to the next bit. One of the things that is very important in cleaning is you actually have to rinse your wafer. Just like you rinse your clothes after you wash them with soap, right? You rinse to get rid of all the chemicals so that no residue is left behind. This rinsing takes an enormous amount of water. In fact, the fab that Tatas are trying to build in Gujarat will probably take as much water as the city of Ahmedabad. So fabs are very water hungry. And that some of you, I think, sort of asked that how to be judicious with that water use, how to reduce the usage of water, how to reduce the usage of chemicals is an ongoing concern that many fabs are trying to handle. So for example, one of the things that people are trying to do is people have sort of realized that cleaning is done so often in the fab. It's one of the most repeated things that we do in the fab. Okay. So what they're trying to do is if you can save even say, instead of taking 1 liter, if you it can reduce the usage of water by around 20%. Because of the number of times you use the cleaning solution, you actually can really reduce the water usage. So one of the ways that people are trying to do is come up with these advanced cleans where they take the RCA clean, but make it simpler, make it use less chemicals, make it use less time, maybe make it use less water. And this has become its own research field. I'll not go into details, but I just want to highlight. So this is what the traditional RCA clean looks like. There is a tank for each cleaning, and between two cleans, there is a rinse cycle, there is a dry cycle, etc., etc. So you need this many tanks to do an RCA clean. When you go to diluted chemistry, you can simplify it further. When you go to some interesting reduced cleans, some modern cleans, you can reduce this even further. What industry is rapidly, however, moving towards is what is called a single wafer, single tank clean, where the wafer just sits in one chuck, it rotates, chemicals are dispensed on the top of it, and the wafer gets clean. Gone are the days where they would be done in a batch process by dunking it all in tanks. Okay. And again, I don't have time to sort of go through details, but there's very good examples that single wafer cleans, single tank cleans are the way to go to the future, and most wet processing is going in that direction today. Okay. All right. Quick questions. 440. How am I doing? But I'm actually from civil department and any difficulty in the concept. So what do you recommend? I mean, just keep an open mind. Much of what I'm saying is actually just 11th and 12th grade. I'm not actually asking for very deep concepts. But if you are finding it tough, just read up about it. I have NPTEL lectures which have more details. They are being soluble into what? Water. They are being soluble into water. What are the properties of silicon 100 for using it in CMOS? Electronic properties of silicon, but more important than electronic properties is the silicon-silicon dioxide interface that I've already highlighted. And lastly, the scale. We know how to work with silicon, or there are manufacturers who will give you solutions for silicon. That kind of, let's call it, maturity is not there in other wafers technologies. So we are getting different grade during zone refining. Why can't we keep refining until we get the all in the same grade? If you look at the zone refining into detail, you sort of realize that impurities cannot get do not get destroyed, right? So all you can do is take impurities from one place and move it to the other. There's nothing like eliminating impurities. I know it sounds silly, but why we make wafer in round shape and not square? It makes people are trying to make square shaped wafers, by the way. It's just that the way the wafers are made, they naturally come out round. So if you want to make square, what you have to do is make it bigger round and then cut the corners away. But solar cell people are trying to do it for a while now. All right, let's move on. So that's cleaning. So the most important part of cleaning is there is a certain chemistry that we use. Water is a big issue and reuse of water is a big issue. So that is why industry is moving towards single tank cleans. All right, let's then go to wafer clean room. Now I'm doing doping. Now I'm doing on time. So with that, we will now move to, okay, no, wrong one. Good, doping. So let's now talk doping. Probably one of the most important modifications that we do to silicon wafers, okay? So what is doping? So silicon, pure silicon is basically just silicon, right? There's nothing else. Now, this has great properties, but sometimes what makes semiconductor industry, semiconductor interesting is not that it has moderate conductivity. What makes it interesting is that you can change its conductivity. So one of the ways in which we change the conductivity of silicon is by adding certain impurities, but these impurities are different than the impurities we have discussed till now. These are deliberate impurities that change the property in predictable ways. For example, you take a silicon and you add antimony to it or phosphorus to it. Now, phosphorus and antimony are group 5 elements. So they have one extra electron in the outermost shell than silicon. So when they bond to silicon, that one electron becomes free to contribute to conductivity and free to make the material more conductive. This is called N-type doping because it has an extra electron. You can do the same thing with a group 3 material like boron, and that has one less electron than silicon. So instead of creating an extra electron, it actually creates a hole, a lack of electron, which can be thought of as a positive charge, and that basically called p-type doping. So this is basically the general idea of N and p-type doping, and doping is routinely used in semiconductors to make junctions, and those junctions have electric fields, and those electric fields can then be used to move the carriers in certain directions. This is what sort of creates a device that has certain use, because the electric field can be created and the electric field will then push the electrons in a certain direction. How those electric fields are created, how those things happen, many people have gone through PN junctions in their 11th and 12th grade, but that's not necessary to understand the rest of this lecture. Just that we need to introduce dopants. Now, there are two ways of introducing dopants. One is we can deposit something on top through CVD. That we will discuss later. The other is that we can introduce the dopants in the wafer through diffusion, and that is what I'm going to discuss today. Now, dopant diffusion, frankly speaking, is not an important technology today, but it's an important concept because the idea of diffusion comes up in semiconductors again and again, and this is a good place to introduce it. Okay. What is commercially used in modern industry is not diffusion, it's implantation. We will also discuss that. Okay. What is the basic idea of a dopant of diffusion? It basically is very simple. Things tend to go from high concentration to low concentration. So that is all that this equation basically, which is called Fick's second law of diffusion, basically states that things will move in time given the derivative of their given the gradient. So things go from high concentration to low concentration. That's basically it. The rest all is math. So what that basically means, if I take silicon and I introduce dopants on the front surface, then there is high concentration of dopants on the surface. There is zero concentration of dopants inside. Provided I can heat this up to some reasonable temperature so things become mobile, dopants will automatically diffuse from high concentration to low concentration. Like there's no magic that I have to do. Things will just go from high concentration to low concentration. The rate at which they do that is measured by something called diffusivity, or D, diffusion coefficient. This diffusion coefficient is extremely sensitive to temperature. It's exponentially depends on temperature. So usually what happens is the diffusion doesn't happen at room temperature or it's too slow. But as soon as you heat the wafer, the diffusion increases rapidly and then things start moving in very quickly. So this is how we introduce dopants inside silicon. Put the dopants on the surface and heat it up. Okay. This is what I was trying to tell you, that dopant diffusivity is exponentially dependent on temperature. So temperature is an extremely sensitive sort of handle to change the movement of ions inside. Now, there's a hidden detail here that we sort of have to appreciate. Not all things need to diffuse inside silicon. For example, okay, my animations are off. There are things that we want to diffuse. For example, dopants, right? So this is an example of dopants: boron, phosphorus, arsenic. These are things we wish will move inside silicon. And they have certain diffusivity. That is a function of temperature. And there are certain things we don't want to move. For example, this is all the junk. This is all the metal impurities, chromium, gold, iron, stuff that really sort of kills the properties of silicon. We don't want them to diffuse. They also have certain diffusivity as a function of temperature. The goal of any successful diffusion process would be that we diffuse the stuff we want to diffuse and we don't diffuse the stuff that we don't want to diffuse.